63 light-years away from Earth, there is a place that changed everything we thought about planets. This world is called HD 189,733b, and it looks beautiful and blue like our planet when seen from far away. But the discovery made by scientists was shocking. It turns out that on this planet it does not rain water like here, but rather sharp little pieces of glass that fly through the sky at more than 8,000 kilometers per hour, cutting everything in their path. The winds there are so strong they can destroy anything in seconds. The temperature reaches more than 1,000 degrees, hot enough to melt metal. Prepare to sleep while listening to this video and discover the secrets of this impossible world. Subscribe to the channel. Leave your like and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Imagine a world where the sky rains shards of glass sideways, driven by winds faster than sound. This isn't science fiction. It's the shocking reality of a planet called HD 189,733b, whose discovery forever changed how we view alien worlds. Back in 2005, astronomers using the transit method spotted this distant planet, and it quickly became a cornerstone of exoplanet science. The transit method involves watching for tiny, periodic dips in a star's brightness as a planet crosses in front of it. For HD 189,733b. These transits were a goldmine of information because the planet orbits very close to its star, completing a full revolution in just over 2 days. This frequent passing, combined with the star's relative brightness and the planet's proximity to Earth at about 63 light-years away, made it an ideal laboratory for detailed observations. But the real breakthrough came when scientists realized they could use these transits to study the planet's atmosphere. As starlight filters through the atmospheric layers during a transit, different gases and particles absorb specific wavelengths of light. By analyzing this light with spectroscopy, astronomers can decode the atmospheric composition, much like reading a chemical fingerprint. When researchers applied this technique to HD 189,733b, they found something extraordinary: the clear signature of silicate particles. Silicates are common on Earth, forming rocks and sand, but here they were detected in the atmosphere of a gas giant planet. This was a monumental discovery because it marked one of the first times astronomers had directly identified specific compounds in an exoplanet's atmosphere. The presence of silicates hinted at extreme conditions, with temperatures soaring high enough to vaporize rock and then condense it into tiny droplets. This led to the startling conclusion that the planet likely experiences rain made of molten glass, a phenomenon unlike anything in our solar system. The detection was made possible by advanced instruments on telescopes like the Hubble Space Telescope, which captured high-resolution spectra during transits. The data revealed that silicates exist in the atmosphere as a fine mist or haze, scattering light in ways that also help determine the planet's deep blue color, though that beauty masks its violent nature. This discovery wasn't just about finding another planet. It revolutionized the field by proving that we could move beyond mere detection to characterize alien environments in depth. Before HD 189,733b, exoplanet studies primarily focused on identifying new worlds through methods like radial velocity or transit photometry, but atmospheric analysis was rare and challenging. This planet demonstrated that with the right conditions, a bright star, a close orbit, and relative proximity to Earth, we could glean intimate details about climates and compositions light years away. The finding opened the floodgates for similar studies on other exoplanets, turning HD 189,733b into a benchmark for comparative planetology. It showed that gas giants outside our solar system could host weather systems and chemical processes far more exotic than those on Jupiter or Saturn. For instance, the silicate signatures suggested that the planet's atmosphere operates like a massive, continuous furnace where materials vaporize, condense, and precipitate in a relentless cycle. This insight forced scientists to rethink their models of planetary formation and evolution, considering how intense stellar radiation and tidal locking could create such infernal conditions. The discovery also highlighted the importance of the transit method as a tool for atmospheric spectroscopy, paving the way for future missions and telescopes aimed at studying habitable zones and potential biosignatures. Moreover, it underscored the value of persistent observation campaigns, as multiple transits provided enough data to confirm and refine these findings. The team behind the discovery included researchers from various international institutions, who collaborated to analyse the spectral data and publish their results, sparking widespread interest in the exoplanet community. As news spread, HD 189733b captured public imagination, symbolising the strange and often hostile diversity of planets in our galaxy. Its story is a testament to human curiosity and technological ingenuity, showing how we can uncover hidden realities across vast cosmic distances. In the years since, this planet has remained a prime target for further study, with observations confirming additional atmospheric components like water vapour, methane, DOT, and carbon dioxide, though these are overshadowed by the extreme heat and violence. Each new observation builds on that initial 2005 discovery, deepening our understanding of planetary science. The legacy of HD 189733b is that it transformed exoplanet research from a numbers game into a detailed exploration of alien worlds, proving that even the most nightmarish planets can teach us invaluable lessons about the universe. This journey of discovery reminds us that space is full of wonders that challenge our expectations and expand the boundaries of knowledge. So, after all that talk about its discovery and violent weather, you might think we have a handle on this planet, but hold on, because its most famous feature is a cosmic trick. When scientists first managed to determine the colour of HD 189733b, they found a deep, azure blue dot, a hue that instantly reminds us of our own Earth as seen from space. That familiar shade evokes images of peaceful oceans and a life-giving atmosphere, a potential haven in the void. But here is the cruelest deception in the cosmos. That beautiful blue is not a sign of water or tranquility. It is the colour of a raging, superheated atmosphere filled with a haze of microscopic silicate particles. These are not gentle clouds of water vapour. They are a tempest of tiny, molten glass fragments. The process that creates this colour is called Rayleigh scattering, the same basic physics that makes our sky blue. But the ingredients are utterly alien. On Earth, sunlight interacts with molecules of nitrogen and oxygen, scattering blue light more effectively and painting our heavens. On this distant world, the star's light slams into countless fine particles of silicate, which scatter blue light with ferocious efficiency. Think of it like a perpetual, planet-wide sandstorm. But the sand is vaporized rock, and the grains are so small they selectively bounce blue light into space. This is why, from a distance, the planet appears as a serene blue marble. The measurement of this color was a feat in itself, achieved by observing the subtle changes in reflected starlight as the planet orbited its star. Scientists used the Hubble Space Telescope to analyze the light, noticing a tiny dip in blue wavelengths when the planet was behind its star, confirming that the blue light was coming from the planet itself. This was not an easy observation. It required immense precision and patience. The result was a colour that is actually a bit more cobalt and deeper than Earth's soft azure. But do not let that beauty fool you for a second. This blue sky is a killing field. Those same silicate particles that create the lovely colour are the raw material for the planet's horrific glass rain. They are suspended in an atmosphere so hot it can vaporise metal, whirled around by winds that move at thousands of miles per hour. The serene blue mask hides a reality of unimaginable violence. This discovery was a watershed moment for exoplanet science because it taught us a brutal lesson about first impressions. We are hardwired to look for Earth twins, for planets that look like home. We see a blue dot and our minds jump to oceans, clouds, and potentially life. HD 189733b shatters that analogy completely. It is the ultimate example of why we cannot trust appearance alone in the search for habitable worlds. A blue planet can be a hellscape, a furnace with a beautiful, deadly facade. This has profound implications for how we interpret data from future telescopes. When we point the James Webb Space Telescope or other future instruments at distant exoplanets, one of the first things we might determine is their colour. If we see blue, we now know to temper our excitement immediately. It could be water, or it could be a sky full of abrasive, glassy hail. The colour blue is no longer a reliable biosignature. It is merely a clue that must be investigated with other methods. We have to look at the atmospheric composition, the temperature, the orbit. We need to search for the chemical fingerprints of gases like oxygen or methane in combination with other factors. The lesson from this planet is that the universe is a place of infinite variety and often infinite deception. It forces astrobiologists to be more cunning, to develop better tools and models to distinguish between a living world and a beautiful corpse. This world is a gas giant, similar in broad structure to Jupiter, but its atmosphere is a chemical cocktail from a nightmare. Beyond the silicates, spectroscopy has detected traces of water vapour, methane, DOT, and carbon dioxide, but these are utterly irrelevant for life as we know it. The temperatures are simply too high for any complex chemistry to survive. The silicate haze dominates the visual appearance and the physical processes. The particles are not static. They are caught in a violent cycle of vaporization and condensation. On the day side, permanently locked towards the star, temperatures soar high enough to turn sand into gas. These silicate vapors are then carried by those insane winds to the cooler night side, where they condense directly into droplets of molten glass. This is the source of the particles that scatter the blue light. So, the very thing that makes the planet beautiful is a direct product of its most extreme punishment. It is a self-perpetuating cycle of horror. The winds, clocked at over 5,000 miles per hour, ensure that this haze is global, enveloping the entire planet in its deceptive blue shroud. There is no safe place on this world, no calm eye in the storm. The entire atmosphere is the storm. This also affects how heat is distributed across the planet. The blue colour means a lot of energy is being scattered back into space, but the immense greenhouse effect from other gases traps enough heat to maintain the infernal temperatures. It is a complex and brutal energy balance, nothing like the relatively gentle climate of Earth. Understanding this helps scientists model other hot Jupiter exoplanets, many of which might share similar characteristics. We now know that a common type of planet in the galaxy could be these blue, hellish worlds, all hiding their true nature behind a veil of familiar colour. This realization is humbling. It expands our definition of what a planet can be and forces us to abandon our Earth-centric biases. The search for life becomes more challenging, but also more interesting. We cannot just look for pale blue dots. We have to look for the right kind of pale blue dot. Or perhaps we need to look for other colours altogether. Maybe a truly habitable world has a subtle, unique colour signature we have not yet identified. HD 189733b serves as a constant reminder of the universe's creativity in designing environments of extreme violence. Its blue colour is a masterpiece of cosmic misdirection, a warning that not all that glitters is gold, and not all that is blue is water. It is a planet that looks like a friend but is the ultimate enemy, teaching us to dig deeper, to question our assumptions, and to appreciate the sheer strangeness that exists in the cosmos. As we continue to explore, we will carry this lesson with us, making our search for another Earth more careful, more nuanced, and ultimately, more likely to succeed because we will not be fooled by a pretty face again. The story of this planet's colour is a cornerstone in modern astronomy, a simple observation that unravelled a complex truth about the diversity of worlds and the importance of looking beyond the surface. It is a tale that started with a beautiful blue image and ended with the understanding of a perpetual, glass-sharp storm, a fundamental shift in how we see the universe around us. So, we have established that its beautiful blue colour is a lie, a cosmic facade hiding a truly monstrous reality. But to understand why this planet is such a nightmare, we need to look past the colour and dive straight into what that atmosphere is actually made of. It is not a mix of nitrogen and oxygen like we breathe. It is a toxic, superheated soup of chemicals under pressures and temperatures that defy imagination. The air itself on HD 189733b is a deadly cocktail, a swirling maelstrom where familiar substances become irrelevant and exotic ones dominate. When astronomers point their most powerful telescopes, like the Hubble Space Telescope, at this world, they use a technique called spectroscopy to dissect the starlight that filters through the planetary atmosphere during a transit. This allows them to identify the unique fingerprints of different molecules and elements. What they found was both fascinating and terrifying. Yes, there are traces of water vapour, along with molecules of methane and carbon dioxide, on another world, in a different context. These could be signs of interest, perhaps even hints of biological processes, but here they are utterly meaningless. The extreme heat, which soars to thousands of degrees, renders them nothing more than background noise in a much more violent chemical symphony. The true star of this horrific show, the component that defines the planet's deadly nature, is silicate. Silicates are the building blocks of rocks on Earth. They are what make up sand, quartz, and most of the Earth's crust. But on HD 189733b, they are not solid. The intense heat from the nearby star, which blasts the planet with relentless radiation, is so extreme that it vaporizes these silicate materials. They do not exist as rocks or sand grains. Instead, they are suspended in the atmosphere as a fine, oppressive haze of vaporized rock. Think of it as a fog, but a fog made of the same stuff as glass, heated until it turns into a gas and then condensing into tiny particles. This silicate haze is not uniform. It is a dynamic, churning layer that interacts with light and heat in profound ways. The temperatures on the planet are so high, well above 1,000 degrees Celsius, that these silicates are not just melted, they are fundamentally altered, existing in a state between vapour and liquid. This is the key ingredient for the planet's infamous weather. When conditions are right, specifically when these silicate vapours are carried by winds to slightly cooler parts of the atmosphere, they begin to condense, but they do not form nice, crystalline structures like sand. Instead, because of the rapid cooling and the turbulent environment, they form droplets of molten glass. This is the origin of the glass rain. So, the atmospheric composition is directly responsible for the most dramatic phenomenon on the planet. But it is not just silicates alone. The atmosphere is primarily composed of hydrogen and helium, much like Jupiter, but the intense stellar irradiation cooks this basic mixture into something far more exotic. The high temperatures break apart molecules, allowing for the formation of various metal vapors and other compounds that would not be stable on cooler worlds. Elements like iron, magnesium, and sodium are likely present in gaseous form, adding to the toxic brew. These metals can contribute to the coloration and the overall opacity of the atmosphere, absorbing and scattering light in complex ways. The silicate particles themselves are probably not pure. They likely contain impurities from these other elements, which could affect their properties, such as their melting point and how they scatter light, contributing to that deceptive blue hue. The process of detecting these components is a marvel of modern science. Spectroscopy does not just tell us what is there, it can also give clues about abundance and distribution. By analysing how much light is absorbed at specific wavelengths during a transit, scientists can estimate how much of each substance is present in the atmospheric column. For HD 189733b. The silicate signatures were unmistakable, showing up in the infrared part of the spectrum where these particles absorb and emit radiation. This was a landmark discovery because it was one of the first direct detections of cloud particles in an exoplanet atmosphere, and it confirmed that clouds on other worlds can be made of truly alien materials. The presence of this silicate haze has major implications for the planet's energy balance. Clouds on Earth reflect sunlight and trap heat, influencing our climate. On this exoplanet, the silicate haze probably plays a similar role, but in a much more extreme manner. It might help to scatter some stellar radiation back into space, contributing to the colour we see, while also trapping heat underneath, exacerbating the greenhouse effect and helping to maintain the scorching temperatures. This creates a feedback loop where the heat vaporizes more silicates, which then form clouds that affect the heat distribution, and so on. It is a self-sustaining cycle of violence. The atmospheric composition also tells us about the planet's formation and evolution. The fact that silicates are so abundant in the atmosphere suggests that the planet either formed with a rich supply of these materials or that it is actively evaporating from a rocky core deep within. As a gas giant, it might have a solid core somewhere beneath the thick layers of gas, and the extreme heat could be slowly stripping away material, enriching the atmosphere with vaporized rock. This ties into the concept of atmospheric escape, where the planet is losing mass over time due to the stellar radiation. The composition is not static. It is dynamic and changing, driven by the relentless energy input from the star. Comparing this to planets in our solar system highlights how alien it is. Jupiter has clouds of ammonia and water, with violent storms, but nothing that approaches the concept of vaporized rock rain. The atmospheric chemistry on HD 189733b is operating in a regime that we have no direct experience with, which is why it serves as such a valuable laboratory for testing our models of physics and chemistry under extreme conditions. Scientists use complex computer simulations to try and replicate these conditions, inputting what we know about the temperature, pressure, and stellar flux to see if they can reproduce the observed spectral features. These models help us understand not just this planet, but the whole class of hot Jupiters, which are surprisingly common in the galaxy. Many of these worlds might have similar silicate clouds and extreme weather, meaning that HD 189733b could be representative of a whole category of hellish planets. The deadly composition also directly impacts any remote sensing we do. When we look for habitable worlds, we often search for biosignatures like oxygen or methane in specific combinations. But this planet shows that abiotic processes can create complex atmospheric chemistries that might mimic life signs in the wrong context. For instance, the presence of methane and water vapour together might on another world be interesting, but here we know it is purely due to thermal and chemical processes without any biology involved. This teaches us to be cautious and to look for multiple lines of evidence when assessing potential habitability. The study of this atmosphere is ongoing. With new telescopes like the James Webb Space Telescope, we are getting even more detailed spectra. Webb's infrared capabilities are perfect for probing deeper into the atmospheric layers, potentially mapping the temperature and composition variations across the planet's different regions. We might discover new compounds, better understand the size and distribution of the silicate particles, and learn how they interact with the insane winds that whip around the planet. Every new observation adds a piece to the puzzle, helping us refine our understanding of this deadly chemical cauldron. In the end, the atmospheric composition of HD 189733b is a story of transformation, where ordinary materials like sand are turned into a vaporized haze that fuels a perpetual storm of glass. It is a reminder that the universe can take the familiar and make it utterly alien, and that the conditions for life are incredibly specific. By studying this hostile environment, we not only satisfy our curiosity about the extremes of nature, but also better define the boundaries within which life might possibly exist elsewhere. The deadly air of this distant world, with its vaporized silicates and metal vapors, is more than just a scientific curiosity. It is a lesson in humility and a guidepost in our ongoing search for other worlds, showing us just how diverse and often inhospitable planets can be. Now, having delved into the toxic chemical soup that makes up its atmosphere, let's get into the real action. How does that vaporized rock actually turn into the legendary glass rain? This isn't just a simple matter of stuff getting cold and falling down. The physics behind this precipitation is a brutal dance of thermodynamics and fluid dynamics playing out in conditions we can barely simulate. It all starts with those silicate vapours we talked about, the ones that give the planet its deceptively beautiful blue hue. These aren't just floating around passively, they are caught in a relentless cycle of violence. The process begins on the day side of the planet, the hemisphere permanently locked facing the star, where temperatures are so obscenely high that any solid material gets blasted into a gaseous state. Here, the silicates exist as a superheated vapour, mixed in with hydrogen and other gases. But the atmosphere isn't static. It's a churning, convulsing fluid, powerful updrafts, fueled by the immense heat, carry this vapour high up into the atmospheric layers. As these parcels of gas rise, they inevitably move towards slightly cooler regions. Now, cooler is a relative term here. We're still talking about temperatures that could melt iron, but it's just enough of a drop to trigger a phase change. This is where the magic, or rather, the horror, begins. The silicate vapour, upon hitting these specific altitude bands where the temperature and pressure are just right, doesn't have time to form nice, orderly crystals. Instead, it undergoes rapid condensation, directly forming countless trillions of microscopic droplets of molten glass. Think of it like the water vapour in Earth's clouds condensing into raindrops. But instead of water, it's liquid rock. And instead of a gentle process, it's a violent, instantaneous shift. These newly formed droplets are immediately seized by the most ferocious winds in the known galaxy. We're not talking about a strong gust. We're talking about winds that scream across the planet at speeds exceeding 8,000 kilometers per hour. That's more than 7 times the speed of sound here on Earth. These winds don't allow the droplets to fall in a gentle shower. They whip them horizontally, transforming what would be rain into a relentless, sideways sand-blasting of molten glass. The droplets are so small and the winds so fast that this precipitation isn't a fall. It's a scorching, abrasive haze moving at ballistic velocities. It would be like standing in a hurricane where the rain is made of tiny, white-hot projectiles. Now, as these droplets are hurled through the atmosphere, they begin to cool further, but the environment is so turbulent, with shear forces and rapid temperature fluctuations, that the solidification process is anything but smooth. On Earth, when lava cools slowly, it forms crystalline structures like those found in granite, but when it cools extremely quickly, as in when it hits water, it forms the amorphous, chaotic structure of volcanic glass like obsidian. That's exactly what happens here. But on a planetary scale and in mid-air, the molten glass droplets cool in a matter of seconds, frozen in time by the chaotic winds into irregular, sharp dot and jagged shards. There's no time for atoms to arrange themselves into a lattice. They are locked into a random, disordered state, creating particles that are inherently sharp and abrasive. This isn't smooth, polished glass like a window pane. It's more like a mist of microscopic, razor-sharp fragments. The physics of this rapid cooling, driven by extreme turbulence, is what forges these natural blades. And the journey doesn't end there. This horizontal storm of glass doesn't just hit a surface and stop. Remember, HD 189733b is a gas giant. There is no solid surface to speak of, at least not one we could recognize. As the blizzard of glass is driven by the winds, it eventually circulates back towards the hotter regions of the planet, particularly the day side. As it descends into these deeper, infernally hot layers, the temperature rises dramatically. Before these glass shards can travel much further, they encounter heat so intense that they don't even melt. They undergo sublimation, turning directly from a solid back into a vapor. This completes the cycle. It's a hellish version of Earth's water cycle. We have evaporation, condensation, precipitation, and then re-evaporation. But instead of life-giving water, it's death-dealing glass. This continuous loop means the atmosphere is in a constant state of recycling its own brutal building materials. The silicates are vaporized, condensed into glass, and then vaporized again, over and over, in a perpetual, planet-wide manufacturing process for sharp, flying debris. The energy driving this entire cycle comes from the immense temperature difference between the day and night sides, a gradient that powers those supersonic winds which, in turn, govern the precipitation pattern. It's a tightly coupled system where the thermodynamics of heat transfer directly creates the conditions for this unique form of precipitation. Scientists study this by using complex computer models that simulate fluid dynamics and chemistry under extreme pressure and temperature. They input what we know about the planet's orbit, its stellar radiation, and its atmospheric composition, and the models spit out predictions about wind patterns and cloud formation that remarkably match our observations. This tells us that the physics, while extreme, is still governed by the same fundamental laws we understand from Earth. It's just operating in a regime we never see at home. The existence of this glass rain has profound implications for how we think about weather on other worlds. It shows that precipitation isn't limited to water, ice, or methane under the right conditions. A planet can have a meteorological cycle based on literally any substance that can vaporize and condense within its temperature range. This expands the imagination for what kind of strange storms might be happening on the thousands of exoplanets we've discovered. Furthermore, understanding this process helps us interpret data from other hot Jupiters. When we see certain spectral signatures or light curves, We can now consider the possibility of silicate clouds and glass rain as a potential explanation. It makes our models of exoplanet atmospheres more robust and diverse. The violence of this precipitation also means that any notion of a probe or spacecraft ever visiting this world is pure fantasy. Even if we could build something that could withstand the heat, the erosive effect of a constant, high-speed sandblasting by glass shards would strip away any protective shielding in moments. It is the ultimate expression of an uninhabitable environment, where the very weather is a weapon. In a way, the physics of glass rain on HD 189733b is a testament to the universe's creativity. It takes simple processes, condensation, wind, solidification, and combines them in such a way to create something both terrifying and fascinating. It's a reminder that the laws of nature are universal, but their manifestations can be infinitely varied, and often infinitely more hostile than anything we can conceive on our own pale blue dot. By studying this extreme phenomenon, we don't just learn about one weird planet. We learn about the boundaries of physical possibility and gain a deeper appreciation for the relative calm and safety of our own world's weather systems. The sheer violence of that glass rain we just discussed is unimaginable. But it's crucial to understand that those shards aren't just falling, they are being hurled. And that brings us to the immense power behind the throw, the winds. These aren't just strong breezes, they are the defining, dominant force of the entire planet, an elemental power that shapes every single process in the atmosphere. We measure wind speed here on Earth in miles per hour or kilometers per hour, and we think of a Category 5 hurricane as the peak of destructive force with winds around 150 miles per hour. Now, completely erase that scale from your mind. The winds on HD 189733b have been measured at speeds reaching up to 8,700 kilometers per hour. To put that into a perspective that is almost impossible to grasp, that is more than 7 times the speed of sound here on Earth. Let that sink in for a moment. The sound barrier is a physical limit that supersonic jets struggle to break, creating sonic booms with immense energy. On this planet, the wind doesn't just break the sound barrier, it shatters it into a million pieces, moving at hypersonic velocities that make our most powerful storms look like a gentle sigh. These winds are so fast that they are nearly 6 times more powerful than the strongest winds ever recorded on Jupiter, which itself is a planet famous for its perpetual, raging storms like the Great Red Spot. So, what could possibly generate and sustain such insane, continuous wind speeds? The answer lies in the most fundamental driver of weather anywhere in the universe: heat, specifically. An absolutely colossal and relentless temperature difference. HD 189733b is tidally locked to its star, meaning one side, the day side, is permanently cooked under blistering radiation, with temperatures soaring above 1,000 degrees Celsius. The other side, the night side, is plunged into eternal darkness. Now, it is not cold by any earthly standard. It is still horrifically hot, but it is significantly cooler than the day side. This creates a staggering temperature gradient, a difference of hundreds of degrees between the two hemispheres. In any fluid system, and an atmosphere is essentially a giant fluid, such a massive imbalance in heat creates a massive imbalance in pressure. Air, or in this case DOT, a thick soup of hydrogen and silicate haze, always moves from areas of high pressure to areas of low pressure, trying to equalize the system. On this planet, the day side is a colossal high pressure zone, and the night side is a vast low pressure zone. The atmosphere responds to this perpetual, extreme pressure difference with a furious, global scale flow. It doesn't just create winds, It creates a phenomenon known as superrotation, where the entire atmosphere itself rotates much faster than the planet spins on its axis. In fact, the planet's rotation is locked, but its atmosphere is whipping around it in a continuous, violent attempt to transfer heat from the scorching day side to the slightly less scorching night side. This is not an occasional storm. This is the permanent, baseline state of the planet's weather. The winds are the planet's method of thermoregulation, a desperate but futile attempt to balance the unbalanceable. They flow from the day side to the night side in a global current. But because of the planet's rotation and complex fluid dynamics, they get channeled into these incredibly fast, jet stream-like bands that encircle the planet. Imagine a river of air moving faster than a bullet, and that river is thousands of miles wide and wraps around the entire globe. This constant dot, supersonic flow is what picks up the condensing silicate droplets and turns them into that horizontal, glassy shrapnel. Without these winds, the glass might simply condense and fall, but with them, it becomes a scorching, abrasive sandblaster that never stops. The winds don't just carry the glass, they are intimately involved in its formation. The incredible shear forces and turbulence within these wind streams contribute to the rapid cooling and solidification that creates the sharp, jagged shards instead of smooth droplets. They churn the atmosphere, ensuring that the silicate vapours are constantly mixed, lifted, cooled, and then hurled back into the heat. This is a fully integrated system where the wind is not a separate phenomenon, but the engine of the entire atmospheric nightmare. Measuring these winds was another triumph of remote sensing. Astronomers didn't just guess. They used the Doppler effect on the light coming from the planet. By carefully analysing the subtle shifts in the spectral lines of various gases in the atmosphere as the planet moved in its orbit, they could map the velocity of the atmospheric gases relative to Earth. It is a technique of breathtaking precision, allowing us to measure the speed of winds on a world over 60 light years away. The data revealed that these winds are not uniform. There are likely faster and slower streams, but the average speeds are what defy belief. The energy required to sustain this is drawn directly from the stellar radiation bombarding the day side. It is a direct conversion of stellar heat into kinetic energy on a scale that is almost incomprehensible. This understanding helps us model other tidally locked planets, especially hot Jupiters. We now know that if a planet is close enough to its star to be locked, and has a significant day-night temperature contrast, it will almost certainly develop super-rotating winds, though perhaps not always this extreme. The winds on HD 189733b represent an upper limit, a case study in atmospheric dynamics pushed to the absolute extreme. They also have implications for the planet's long-term evolution. Such violent circulation must mix the atmospheric layers profoundly, potentially dragging heavier elements from deep below and vaporizing them in the upper atmosphere, which might contribute to the slow evaporation of the planet over billions of years. The winds ensure that the atmosphere is well mixed, a homogeneous hell from top to bottom, for any hypothetical future exploration. These winds represent an insurmountable barrier. No probe could hope to maintain stability or structural integrity in such an environment. The friction alone would generate immense heat, and the physical force would tear any object apart instantly. They are a testament to the fact that some places in the universe are simply not meant to be visited, only observed from a safe and immense distance. In the end, the winds of HD 189733b are more than just a weather phenomenon. They are the planet's heartbeat, a furious, relentless pulse that dictates its entire existence. They are the reason the blue haze is global, the reason the glass rain is horizontal, and the reason the heat is distributed in a way that maintains the planet's infernal equilibrium. By studying this atmospheric fury, we learn not just about one world, but about the fundamental principles of fluid dynamics and energy transfer under conditions we can never recreate. It is a humbling reminder of the raw, untamed power that nature can wield when the constraints of our familiar world are removed. That relentless, supersonic wind we just talked about isn't just a standalone force. It is the essential conveyor belt for one of the most bizarre and violent planetary processes ever discovered, the glass cycle. Think of Earth's gentle, life-sustaining water cycle, where water evaporates, forms clouds, rains down, and flows back to the oceans to begin again. Now, imagine a twisted, infernal version of that, where the medium isn't water but silicate rock, and the temperatures are so high that the entire process operates at melting points. This is the hypothetical but compelling glass cycle of HD 189733b, a continuous, planet-wide recycling system for material that turns solid rock into vapor, then into molten glass, and back again, all driven by extreme heat and those unimaginable winds. It is the planet's own version of hydrology, but instead of a water cycle, it is a silicate cycle, a perpetual motion machine of destruction. The cycle begins on the planet's permanent day side, the hemisphere that always faces its star and is baked by relentless radiation. Here, the temperatures are so astronomically high, well over 1,000 degrees Celsius, that they exceed the vaporization point for silicate materials. The same compounds that form sand and rock on Earth are not solid here. They are literally cooked into a gas. This is the first step, vaporization. Silicate rocks, whether from a deep core or suspended in the lower atmosphere, are turned directly into a vapor, a fog of gaseous rock that rises and mixes with the primary atmospheric gases of hydrogen and helium. This vapor is the raw material for everything that follows. But the atmosphere is not still. It is a seething, dynamic fluid. ... The immense heat on the day side creates powerful convection currents, columns of hot gas that surge upwards from the lower, hotter layers towards the higher, slightly cooler parts of the atmosphere. These updrafts are supercharged by the global wind patterns we discussed, which themselves are driven by the brutal temperature difference between day and night. The combination of convection and these supersonic winds acts like a planetary scale elevator, grabbing hold of the silicate vapor and transporting it vertically and horizontally across the globe. As this vapor is lifted to higher altitudes, it enters a region where the temperature, while still scorching hot, is just low enough to allow for a phase change. This is where the magic, or the horror, happens. The silicate vapor doesn't slowly crystallize. It undergoes rapid condensation, in a process similar to how water vapor in Earth's atmosphere condenses into cloud droplets. The silicate gas directly forms countless trillions of microscopic droplets of molten glass. These are not solid yet. They are tiny spheres of liquid rock, superheated and shimmering. This creates clouds, but these are not fluffy water vapor clouds. They are abrasive, glowing clouds of molten silica, a hazy mist of liquid glass suspended in the sky. Now, these newly formed droplets are immediately caught in the grip of those phenomenal winds. With speeds exceeding 8,000 kilometers per hour, the winds don't allow these droplets to fall peacefully. Instead, they are swept along horizontally, creating a global tempest of flying glass. This is the precipitation phase, but it is nothing like rain on Earth. It is a horizontal, blistering sandblasting of molten glass particles moving at ballistic speeds. The droplets are so small and the winds so fast that this rain is more like a scorching, abrasive mist that scours everything in its path. As these droplets are hurled through the atmosphere, they start to cool and solidify. The environment is so turbulent, with rapid changes in temperature and immense shear forces from the wind, that the solidification process is instantaneous and chaotic. There is no time for the atoms to arrange themselves into an orderly, crystalline structure like in quartz. Instead, they freeze into an amorphous, disordered solid, just like how volcanic glass like obsidian forms on Earth when lava cools too quickly. This means the resulting particles are not smooth beads. They are irregular, sharp, dot, and jagged shards, tiny natural blades forged in the planet's atmospheric furnace. This horizontal storm of glass shards doesn't just continue forever. The cycle must complete itself. The winds and atmospheric circulation eventually carry these solid glass particles back towards the hotter regions of the planet, particularly down into the lower atmosphere on the day side. As they descend, they encounter progressively hotter temperatures. Before they can travel much further, they reach a depth where the heat is so intense that it doesn't just melt them, it causes them to sublimate. Sublimation is the process where a solid turns directly into a gas without ever becoming a liquid. So, these sharp glass shards don't melt back into droplets. They instantly transform back into silicate vapor. And just like that, the raw material is returned to its gaseous state, ready to be picked up by convection currents and winds, lifted back to higher altitudes, and condensed once more into molten glass droplets, repeating the entire process over again. This closed-loop system means that the silicate material is constantly being recycled. It is a perpetual cycle of vaporization, condensation, precipitation, and sublimation. It is a hellish, self-sustaining loop that requires no external input other than the relentless energy from the star. This glass cycle has profound implications for understanding the planet's climate and evolution. It explains why the silicate haze is permanent and global. The cycle constantly replenishes it. It also plays a key role in the planet's heat distribution. The clouds of molten glass likely affect the albedo, reflecting some sunlight, while the cycle itself transports heat from the day side to the night side, working in tandem with the winds to moderate, albeit slightly, the extreme temperature contrast. Furthermore, this cycle locks the atmosphere into a specific chemical equilibrium, with a constant fraction of silicates in the vapor and condensed phases. For scientists, this provides a fascinating model to study phase changes and material recycling under conditions impossible to replicate on Earth. It shows that the principles of cycles we see on Earth, like the water or carbon cycles, can apply to utterly alien contexts, just with different materials and energy levels. The violence of this cycle also underscores the absolute impossibility of life or any future exploration. Any complex molecule or structure would be instantly destroyed by the abrasive glass shards or the extreme heat involved in the sublimation process. The glass cycle of HD 189733b is more than just a curious weather pattern. It is a fundamental aspect of the planet's identity, a continuous, violent process that defines its atmosphere and serves as a stark reminder of the diverse and often hostile nature of planets beyond our solar system. By studying this cycle, we gain insights into the potential behaviors of other hot, tidally locked exoplanets, helping us to refine our models and better understand the incredible variety of worlds that exist in our galaxy. Now, after exploring that relentless glass cycle, you might be asking yourself what kind of fundamental force could possibly set the stage for such a perpetual, hellish process. The answer lies not in the atmosphere itself, but in the very foundation of the planet's existence. its brutal gravitational relationship with its star. This is the story of gravity and tidal locking, the ultimate reason why one side of this world is forever burning while the other languishes in an eternal hot night. It all starts with the orbit. HD 189733b whips around its star at an almost incomprehensible speed, completing a full revolution in just 2.2 Earth days. To put that into perspective, our Earth takes a leisurely 365 days to do the same. This incredibly short year is a direct result of the planet's extreme proximity to its host star. It is orbiting so close that the gravitational pull it experiences is immense, forcing it into a tight, fast path that would be unimaginable in our own solar system. This proximity is the key that unlocks everything else about the planet's nature. Because it is so close, the star's gravitational grip is incredibly strong, and this leads to a phenomenon known as tidal locking. You have actually seen this before, right here in our own cosmic backyard. Our moon is tidally locked to Earth, which is why we only ever see one side of it from our planet. The same principle applies to HD 189733b, but on a much more intense scale. Over time, the gravitational forces from the star have acted like a brake on the planet's rotation, slowing it down until it now spins exactly once on its axis for every single orbit it completes around the star. This means the planet's rotation period and its orbital period are the same. The consequence is simple, stark, and devastating. One hemisphere of the planet permanently faces the star, while the other hemisphere permanently faces away into the blackness of space. This is the root of all the chaos we have been discussing, the day side. The hemisphere forever pointed towards the star is subjected to an unending, brutal bombardment of radiation. There is no sunrise or sunset, no cycle of day and night. It is just perpetual, scorching daylight. The temperatures on this side soar to over 1,000 degrees Celsius, hot enough to vaporize metals and, as we know, silicate rock. It is a constant, global-scale furnace where the very concept of solid ground is irrelevant under such heat. Meanwhile, the night side is plunged into eternal darkness. Now, it is crucial to understand that dark does not mean cold in any sense we would recognize. While it is significantly cooler than the day side, it is still horrifically hot, with temperatures likely still in the hundreds of degrees. This is because the planet's insane winds and atmospheric circulation we talked about earlier are constantly pumping heat from the day side over to the night side, preventing it from cooling down dramatically. But that temperature difference, even though both sides are oven-like, is absolutely colossal. We are talking about a difference of several hundred degrees between the two hemispheres. This radical thermal contrast is not just an interesting fact, it is the primary engine that drives the entire planet's insane atmospheric dynamics. In any fluid system, and an atmosphere is a giant fluid, a large temperature difference creates a large pressure difference. The intensely hot day side has a high pressure atmosphere, while the relatively cooler night side has a lower pressure atmosphere. Nature abhors a vacuum and seeks to balance inequalities. So the atmosphere responds to this perpetual pressure imbalance with a furious, global scale flow. The high pressure air from the day side rushes towards the low pressure night side with unimaginable force. This is the direct cause of those supersonic winds we discussed, the ones that reach speeds of over 8,000 kilometers per hour. These winds are not an occasional weather event. They are the permanent, baseline state of the planet's climate, a direct consequence of the tidal locking that creates the eternal temperature divide. They are the planet's desperate, frantic attempt to redistribute the insane amount of heat from the day side. But it is a losing battle because the stellar radiation never lets up. This wind system, in turn, powers the glass cycle, transporting silicate vapours, forming the clouds, and hurling the glass shards across the sky. So, without tidal locking, there would be no constant temperature gradient, no supersonic winds, and likely no global glass storms. The planet's weather is a direct symptom of its gravitational imprisonment. But gravity does not stop there. The intense gravity of HD 189733b itself, which is significantly stronger than Jupiter's, also plays a critical role in shaping the environment. This strong gravitational pull compresses the atmosphere, making it incredibly dense and opaque. This density affects how heat is trapped and how the atmosphere circulates. It also influences the precipitation of those glass particles. In a weaker gravity field, the tiny shards might be able to stay suspended for longer or behave differently. But here, the strong gravity pulls them down more effectively, though the winds are so powerful that they still dominate the movement, creating that horizontal rain. The gravity ensures that the atmosphere is packed tightly, which contributes to its ability to hold heat and maintain the high pressures that drive the winds. The combination of tidal locking and strong gravity creates a feedback loop of extremity. The locking ensures a permanent heat source on one side. The gravity helps maintain a thick, dense atmosphere that can transfer that heat and host complex chemistry. And the resulting winds create the conditions for exotic precipitation. This is why HD 189733b is such a bipolar world, a place of absolute extremes with no middle ground. It is a testament to how fundamental orbital mechanics and gravitational forces can sculpt a world into something so alien. Understanding tidal locking is also crucial for our search for other exoplanets. Many of the worlds we are discovering, especially those close to their stars, are likely tidally locked. This means that the conditions on HD 189733b might not be unique. There could be countless other worlds with permanent day sides and night sides, each with their own bizarre weather patterns driven by similar forces. For planets in the so-called habitable zone, tidal locking presents a complex puzzle. A world might have the right temperature for liquid water on average, but if it is locked, the day side could be a scorching desert while the night side is a frozen wasteland, with only a thin twilight strip in between potentially being habitable. HD 189733b shows us the most extreme possible outcome of this process. A world where the conditions are so harsh that no such temperate zone could possibly exist. The tidal locking is therefore the foundational cause, the first domino that falls, setting off a chain reaction of physical processes that result in the nightmare world we observe. It is a humbling reminder of the power of simple gravitational physics to create environments of staggering complexity and violence. By studying this, we learn not just about one planet, but about a whole class of celestial objects and the fundamental principles that govern their climates. So, the next time you look up at the moon and notice we only see one side, remember that on a much larger and more violent scale. That same simple principle is why a world 63 light-years away has one side that is always burning, forever cooking under the glare of its star, while the other side simmers in a perpetual, hot twilight, together creating the perfect storm for glass to fall from the sky. We have been talking about the planet itself, its locked orbit, its hellish conditions. But to truly understand this world, we must look at the source of all its power and pain, its sun, the star, known as HD 189733, is not a star like our own. It is classified as an orange dwarf, a type of star that is slightly smaller, cooler, and dimmer than our sun. At first glance, You might think that a cooler, smaller star would be a more gentle parent, perhaps offering a milder environment. But that assumption is dangerously wrong. And in the case of HD 189733, it is a complete illusion. This type of star is known for its volatility, for a personality that is far from calm. Orange dwarfs are frequently prone to intense magnetic activity, which manifests as powerful stellar flares and massive sunspots. These are not the occasional solar flares our sun produces. These are eruptions of energy on a scale that can dramatically impact any world orbiting too close. And HD 189733b orbits devastatingly close. The planet is located 30 times closer to its star than the Earth is to the Sun. This proximity is the single most important factor in their relationship, turning what might otherwise be a moderately active star into a weapon of mass destruction aimed directly at the planet. From the planet's perspective, the star would dominate the sky, a giant, swirling orb of orange and red, covered in ever-changing dark spots and frequently erupting with tongues of flame far larger than any seen in our solar system. The planet is so close that it is utterly bathed in the star's radiation, receiving levels of ultraviolet and X-ray radiation that are hundreds of thousands of times more intense than what Earth receives from the Sun. This constant high-energy bombardment has a profound and continuous effect on the planet's atmosphere. The ultraviolet radiation, in particular, is a powerful force for breaking apart molecules. It can tear water vapour, methane, and other compounds apart, ionizing atoms and driving a complex and destructive atmospheric chemistry. This radiation provides the energy to keep the atmosphere stirred up and chemically exotic, helping to maintain the high-altitude haze of silicate particles that gives the planet its blue colour. But the real moments of terror come during the star's flares. When HD 189733 unleashes a stellar flare, it is an event of almost unimaginable power. A flare is a sudden, catastrophic release of magnetic energy, ejecting a wave of radiation and charged particles across space. For a planet as close as HD 189733b, there is no hiding. The planet has no meaningful magnetic field to speak of, so its atmosphere is completely exposed. A large flare would hit the planet's atmosphere like a tsunami. The initial flash of X-rays and extreme UV would blast the upper atmosphere, heating it to even more incredible temperatures and causing it to puff up and expand. This alone can increase the rate of atmospheric escape, literally blowing the outer layers of the planet's air into space. Then, following the light, comes the coronal mass ejection, a cloud of billions of tons of plasma travelling at a significant fraction of the speed of light. When this cloud slams into the planet's atmosphere, it compresses it violently and delivers a massive dose of energy. This can trigger secondary effects like auroras across the entire planet. But these would not be the gentle northern lights we see. They would be a global, violent ionization event that could fundamentally alter atmospheric chemistry on a short time scale. These flares are not rare occurrences. They are a regular part of the star's activity cycle. This means the planet is being periodically cooked by these outbursts, in addition to the constant roasting it already receives. This intense and variable radiation environment is likely a key contributor to the planet's extreme winds. The sudden heating from a flare on the day side could exacerbate the temperature difference with the night side, temporarily whipping the winds into an even greater frenzy. It is a relationship of constant abuse. The star is not just a passive source of light and heat. It is an active, aggressive participant in shaping the planet's environment. This stellar activity also has long-term consequences. The process of atmospheric escape is likely accelerated during these flare events. Observations have indeed suggested that HD 189733b is losing its atmosphere, with hydrogen being detected streaming away from the planet like a comet's tail. Each powerful flare strips away more of the planet's gaseous envelope over billions of years. This could potentially transform the gas giant, leaving behind a stripped-down, rocky core, a ghost of its former self. This teaches us that the evolution of a planet is inextricably linked to the life and behaviour of its star. A star that seems quiet and stable from a distance can be a raging inferno up close, and its activity can make the difference between a world that holds onto its atmosphere and one that is slowly devoured. For astronomers, studying this star-planet system is a unique opportunity to watch stellar activity directly influencing a world in real time. By monitoring the star's brightness, they can detect flares and then look for corresponding changes in the planet's atmosphere during subsequent transits. They might see changes in the spectral signatures of certain elements or a temporary expansion of the atmospheric envelope. This turns the system into a natural laboratory for studying space weather effects on exoplanets. This knowledge is crucial for assessing the habitability of planets around other orange dwarfs, which are common targets in the search for life. While these stars are long-lived and stable for the most part, their flare activity could sterilize planets in their habitable zones, breaking down any complex molecules and stripping away atmospheres. HD 189733b shows us the worst-case scenario. A planet so close that it experiences the full, unadulterated fury of its star. The relationship between HD 189733 and its planet is therefore one of intimate violence. The star made the planet what it is, a tidally locked, overheated, storm-racked hellscape. It provides the energy that vaporizes rock, drives supersonic winds, and forges glass rain. It is both the creator and the destroyer, the engine of every single extreme process we have discussed. Without understanding the active, temperamental nature of this orange dwarf star, we cannot fully understand the nightmare world that orbits it. It is a stark reminder that planets do not exist in isolation. They are products of their stellar environment. And in this case, the environment is one of relentless, brutal hostility. After understanding the relentless fury of its host star, it becomes painfully clear that HD 189733b is the absolute antithesis of a habitable world, a stark example that forces us to completely rethink what we mean by the habitable zone. This planet serves as a brutal lesson in cosmic reality, demonstrating that simply residing in a region where liquid water could theoretically exist on a rocky planet is nowhere near sufficient for life. The conditions here are so profoundly hostile that they redefine the very boundaries of what we consider possible for biology. Let's break down exactly why life, as we know it, is an utter impossibility here. First and foremost, the temperature is the most immediate and obvious deal breaker, with surface temperatures soaring well above 1000 degrees Celsius. This is an environment that doesn't just discourage life, it vaporizes the very building blocks of life. These temperatures are more than enough to melt metals like silver and tin, meaning any complex organic molecule, any strand of DNA, any protein would be instantly torn apart and reduced to its constituent atoms. The heat is not a seasonal variation or an occasional heat wave. It is a permanent, global constant dot, a foundational aspect of the planet's existence. There is no refuge from this thermal inferno. Then we have the atmospheric violence, the constant .z horizontal rain of molten glass shards, driven by winds faster than sound, creates an environment of perpetual erosion and destruction. Imagine trying to assemble a delicate watch in the middle of a sandblaster operating at industrial strength. That is what the formation of any complex chemical structure would be like on this world. The glass rain itself would physically shred any potential molecular assembly, while the supersonic winds would ensure that nothing remains stable or in place for even a fraction of a second. This isn't an environment that is merely challenging. It is one that is actively and continuously dismantling any possibility of order. Add to this the intense stellar radiation we just discussed. The ultraviolet and X-ray flux from the star is hundreds of thousands of times stronger than what Earth receives. This high-energy radiation acts as a constant sterilizing agent, breaking chemical bonds and ionizing atoms. It would prevent the formation of any stable, complex molecules necessary for life, and it would rapidly degrade any that might somehow momentarily form. There is no atmospheric ozone layer to provide protection, no magnetic field to deflect charged particles. The planet's atmosphere is fully exposed to this radiative assault. Furthermore, HD 189733b is a gas giant, which means it lacks a solid surface. This is another critical point against habitability. On Earth, life found niches on the surface, in the oceans, and even deep underground, where environments can be stable and protected. A gas giant has no such stable foundation. There is no ground to stand on, no ocean floor, no subsurface environment where life could shelter from the atmospheric chaos. The entire planet is a thick, swirling fluid of hydrogen and helium, with pressures and temperatures that increase dramatically with depth, eventually reaching conditions where matter behaves in ways we can barely comprehend. There is no conceivable niche where a self-replicating system could establish itself and thrive. The combination of these factors, extreme heat, violent weather, sterilizing radiation, and the absence of a surface, creates a perfect storm of uninhabitability. But the broader lesson here is about the habitable zone itself. Astronomers often define the habitable zone as the range of distances from a star where a planet with a suitable atmosphere could maintain liquid water on its surface. HD 189733b, in a twisted way, might orbit near the inner edge of what could be crudely calculated as a habitable zone for a different kind of planet. But its actual nature as a gas giant in a close orbit makes that calculation irrelevant. This shows that the classical habitable zone is a useful starting point, but it is a dramatic oversimplification. A planet must be the right type, a rocky world with the potential for a stable atmosphere, and it must also be blessed with a relatively calm star. A volatile star like HD 189733 can render even a perfectly positioned rocky world uninhabitable through flares and radiation. Similarly, atmospheric composition is key. A thick, greenhouse gas-rich atmosphere like Venus can create a runaway greenhouse effect, while a thin atmosphere like Mars cannot retain heat or protect against radiation. HD 189733b has an atmosphere that is both toxic and physically violent. This planet forces astrobiologists to refine their criteria. We must now consider factors like stellar activity, planetary mass and composition, atmospheric density and chemistry, and the presence of a magnetic field. We have to look for anti-biosignatures or signatures of abiogenic processes that indicate a sterile environment. For example, the detection of silicate vapor in an exoplanet's atmosphere could be a strong indicator that the world is far too hot for life, regardless of its orbital distance. The study of this hellish world thus makes us better at identifying true candidates for life. By understanding the extremes, we can more accurately define the boundaries of habitability. It teaches us that the universe is capable of creating a vast spectrum of environments, many of which are utterly hostile, and that life likely requires a very specific and narrow set of conditions to arise and persist. This doesn't make the search for life futile. It makes it more focused. We learn to appreciate the incredible fragility and rarity of a world like Earth. Our planet's stable temperature, protective atmosphere, liquid water oceans, and relatively quiet sun are not cosmic defaults. They are a precious and perhaps uncommon combination. HD 189733b stands as a monument to this reality. It is a world that looks beautiful from a distance with its deep blue colour, but that beauty masks a fundamental truth about its nature. It is a place where the laws of physics and chemistry operate without any regard for biology, creating a spectacle of natural forces that is both awe-inspiring and terrifying. In the grand search for other Earths, this planet is a crucial reference point. It represents one end of the exoplanet spectrum, a warning against overly optimistic assumptions. As we develop more powerful telescopes and techniques, we will use the lessons learned from worlds like this to filter out the false positives and hone in on the most promising targets. The impossibility of life on HD 189733b is not a discouraging fact. It is an empowering one. It provides the contrast needed to truly recognize a habitable world when we see one. By studying this inferno, we gain a deeper appreciation for the delicate balance that makes our own world alive, and we become more skilled and discerning explorers of the cosmos. The redefinition of the habitable zone is an ongoing process, and this planet has played a pivotal role in pushing that evolution forward, ensuring that our search for life is grounded in a realistic understanding of the universe's immense and often hostile diversity. After establishing the absolute impossibility of life on this hellish world, a natural and compelling question arises. How on earth, or rather, from Earth, can we possibly know all these intimate details about a planet located 63 light-years away? The answer is a testament to human ingenuity and represents one of the most remarkable feats in modern astronomy: the ability to transform a faint, distant point of light into a rich dataset about an alien world's climate, composition, and physics. This isn't guesswork. It's a sophisticated suite of remote sensing techniques that allow us to act as cosmic detectives, piecing together the story of HD 189733b from across the vast interstellar void. The cornerstone of this effort is a method known as transit spectroscopy. This builds upon the basic transit method used to discover the planet in the first place, every 2.2 days. From our vantage point, the planet crosses directly in front of its host star, causing a tiny, predictable dip in the star's overall brightness. But scientists realized this event was a golden opportunity for much more than just detection. As the planet begins its transit, the star's light doesn't just get blocked. A tiny fraction of that light filters through the planet's atmosphere before reaching our telescopes. Think of it like holding a stained glass window up to the sun. The light passing through carries the fingerprints of every gas and particle it encountered. In this case, the stained glass is the atmosphere of HD 189733b. Molecules in the atmosphere absorb specific wavelengths of light unique to their chemical structure. By using powerful spectrographs, like those on the Hubble Space Telescope, astronomers can spread the starlight out into a rainbow spectrum and look for these tiny, telltale dips in brightness at very specific colours. Each dip is a signature. A dip at the wavelength associated with water vapour means water is present. A dip for sodium means sodium is there. This is how we first identified the presence of water vapour, methane, and carbon dioxide in the atmosphere. And most crucially, how we detected the unmistakable signature of silicate particles. This technique is incredibly challenging because the signal is incredibly faint. the atmospheric filtering effect is about 100 times smaller than the transit dip itself, requiring immense precision and repeated observations to confirm. But the information gleaned is revolutionary, giving us a direct read on the chemical makeup of an atmosphere light years away. Complementing this is another powerful technique called emission spectroscopy, or sometimes secondary eclipse spectroscopy. This method focuses on the light coming from the planet itself. Although the planet is faint compared to its star, it glows with heat, emitting primarily in the infrared part of the spectrum. Scientists observe the system just before and just after the planet disappears behind the star, an event called a secondary eclipse, when the planet is beside the star. Our telescopes see the combined light of both. When the planet is hidden behind the star, we see only the star's light. By subtracting one from the other, astronomers can isolate the faint infrared glow coming solely from the planet. Analysing this planet-only light with a spectrograph reveals another layer of information. The intensity of the glow at different infrared wavelengths tells us about the planet's temperature. More importantly, by taking these measurements at different points in the planet's orbit, scientists can actually create a crude temperature map, revealing the searing heat of the permanent day side and the slightly less intense heat of the night side. This is how we know about the extreme temperature gradient that drives those supersonic winds. The emission spectrum can also reveal the presence of certain molecules and clouds, providing a cross-check on the findings from transit spectroscopy. Another clever method involved simply watching how the planet's apparent brightness changed throughout its entire orbit. By measuring the combined light of the star and planet very precisely, astronomers detected a subtle but consistent change. The system was slightly dimmer in blue light when the planet was at a certain point in its orbit. This was the key to determining the planet's famous blue colour. The reasoning is that the planet reflects more blue light than other colours. So when that blue reflecting hemisphere is fully visible from Earth, the total light of the system has a tiny blue boost. This observation was pivotal because it directly pointed to the mechanism behind the colour, Rayleigh scattering. And since Rayleigh scattering requires small particles, this was a major piece of evidence for the existence of the high-altitude haze of silicate droplets that scatter blue light so effectively. It connected a simple photometric measurement, how bright something is, to a specific physical property of the atmosphere. All of these raw observational data, however, would be just a collection of numbers and graphs without the final, crucial component: complex computational modelling. The real world is messy and complex, and the signals we get from these distant worlds are often ambiguous. Scientists use supercomputers to run massive simulations of exoplanet atmospheres. These models incorporate our understanding of fluid dynamics, thermodynamics, chemistry, and radiative transfer under extreme conditions that we can never recreate in a lab on Earth. Researchers input parameters like the planet's gravity, its orbital distance, the star's energy output, and a hypothesized atmospheric composition. The model then simulates how such an atmosphere would behave, how winds would flow, how heat would be transported, how clouds would form and dissipate. The scientists then compare the output of their simulation, what the planet should look like through our telescopes, to the actual data we have collected. If the model's prediction matches the observed transit spectra, emission spectra, and brightness variations, it gives us confidence that our understanding of the planet's physics and chemistry is on the right track. This is how we can confidently talk about a global glass cycle or winds of 8,000 kilometers per hour. The models that include these phenomena are the ones that best reproduce the real-world observations. These models are constantly refined as new data comes in, creating a virtuous cycle of observation and interpretation. For instance, when the James Webb Space Telescope delivers exquisitely detailed new spectra, modelers will use that data to tweak their simulations, perhaps adding new chemical species or adjusting wind shear parameters to achieve an even more perfect fit and an even deeper understanding. Together, these techniques, transit spectroscopy, DOT, emission spectroscopy, precision photometry, DOT, and advanced computer modelling, form a powerful toolkit that has allowed us to move far beyond mere discovery. We are no longer just finding exoplanets. We are characterizing them. We are studying their weather, analyzing their air, and mapping their climates. The story of HD 189733b, from its deceptive blue colour to its violent glass storms, is a story written in light, a narrative decoded by combining cutting-edge technology with fundamental physics. This entire process underscores a profound truth about modern astronomy. We are no longer passive observers of the cosmos. We are active interrogators, using every tool at our disposal to ask questions of the universe and understand the answers it gives us in the form of photons that have travelled for decades to reach our instruments. The study of this one world has honed these techniques, proving that they work and setting the standard for how we will investigate thousands of other exoplanets in the years to come. It is a breathtaking demonstration that even the most distant and alien worlds are not beyond the reach of our curiosity and our intellect. Now that we have a firm grasp on the advanced techniques used to study this world, it's helpful to put it into context by comparing it to something we know a little better. A planet in our own backyard, Jupiter. You will often hear HD 189733b described as a hot Jupiter. And while that label is technically accurate from a classification standpoint, it can be dangerously misleading, hiding the profound and fundamental differences that make this exoplanet so extreme. Yes, both are gas giants, meaning they are massive planets composed primarily of hydrogen and helium, without a solid surface like Earth's. They share that basic architectural blueprint, but the moment you look beyond that single commonality, the two worlds diverge into entirely separate categories of existence. Jupiter, in our solar system, orbits the Sun at a safe, vast distance, basking in only a faint fraction of the solar radiation that Earth receives. Its cloud tops are bitterly cold, hundreds of degrees below 0 Celsius, and it's famous. Swirling storms are powered largely by internal heat left over from its formation, combined with the energy released as the planet slowly contracts. Its atmosphere, while violent, features clouds of ammonia and water ice, with winds that, though faster than any on Earth, are a gentle breeze compared to what we see elsewhere. HD 189733b, on the other hand, is ferociously heated by its star, orbiting so close that it is literally cooking. This external heating is the dominant energy source, and it completely overwhelms any internal heat the planet might have. The result is an atmosphere that is not just warmer, but radically expanded, chemically exotic, and dynamically insane. The temperatures are not hundreds of degrees below zero. They are hundreds of degrees above the melting point of silver. This intense heat fundamentally alters the chemistry. Instead of the familiar ammonia clouds of Jupiter, we get clouds of vaporized silicate, the same material that makes up sand on Earth. This is the difference between a world with weather and a world with a permanent, global cataclysm. The atmospheric dynamics are also driven by completely different mechanisms. Jupiter, with its relatively uniform exposure to sunlight and its fast rotation, has a weather system dominated by banded jet streams and long-lived storms like the Great Red Spot. HD 189733b, being tidally locked, has a weather system driven by the desperate attempt to transfer heat from the permanent day side to the permanent night side. This creates a single dot, overwhelming pattern of super-rotating winds that scream around the planet, rather than the complex, multi-banded structure of Jupiter's atmosphere. The wind speeds themselves are in a different league entirely. Jupiter's fastest jets can reach around 500 kilometers per hour, which is certainly impressive. But the winds on HD 189733b are more than 10 times faster, exceeding 8,000 kilometers per hour. This isn't a difference of degree, it's a difference of kind. It's the difference between a powerful hurricane and a thermonuclear shockwave. The very nature of precipitation is different. On Jupiter, we might see rain or hail of water and ammonia compounds. On HD 189733b, the precipitation is molten glass, solidifying into sharp shards mid-flight. This comparison highlights that the term hot Jupiter is a useful shorthand, but it can make us imagine a slightly toasty version of Jupiter. The reality is that these worlds are a distinct class of their own, defined by stellar proximity and the extreme physics that proximity unleashes. Studying these differences is incredibly valuable for planetary scientists. By understanding how the same basic planet type, a gas giant, can exhibit such wildly different behavior under different stellar influences, we can build better models for how planets form and evolve. It helps us understand the role of stellar radiation, tidal forces, and atmospheric escape. Jupiter represents a gas giant in its natural state, relatively unperturbed by its star, while HD 189733b represents a gas giant under extreme duress, pushed to its physical limits. This spectrum of possibilities is crucial because it tells us that not all gas giants are alike. The galaxy is likely filled with a vast diversity of such worlds. And HD 189733b is just one example of how extreme they can get. This comparison also helps us appreciate our own solar system. Jupiter acts as a protective giant, its gravity helping to clear the inner solar system of debris, potentially aiding the development of life on Earth. A hot Jupiter like HD 189733b, by contrast, would have wreaked havoc if it had migrated into the inner solar system, likely disrupting the orbits of any terrestrial planets and making life impossible. So, while they share a name, understanding the chasm between a classic gas giant and a hot Jupiter is essential for grasping the true nature of these alien worlds. It reminds us that our solar system, with its orderly arrangement and relatively calm giants, is just one possible configuration in a cosmos full of much more violent and dynamic systems. The study of HD 189733b doesn't just teach us about one planet. It teaches us about the potential fate of gas giants that wander too close to their stellar parents, and it expands our definition of what a planet can be. After exploring the stark contrasts between this exoplanet and the gas giants in our own solar system, it becomes overwhelmingly clear that the existence of HD 189733b is not just a scientific curiosity. It is a profound and necessary reality check in our quest to find life beyond Earth. This world, in all its violent glory, forces us to confront some uncomfortable truths and fundamentally reshape our approach to one of humanity's biggest questions. The most immediate lesson is about deception. We are, by nature, visual creatures, and we tend to look for familiar patterns. When we first determined that this planet was a deep, azure blue, it was a moment that could have easily been misinterpreted. Our brains are wired to see that colour and think of Earth's oceans, of a world brimming with potential. But HD 189733b is the ultimate cosmic bait and switch. Its blue hue is not a sign of water, but a symptom of a raging atmosphere filled with scattering silicate particles. This teaches us a critical, almost brutal, lesson: We cannot trust appearance alone. A planet's colour, its reflectivity, or even its general position in a star system cannot be taken at face value. This realization forces a major shift in strategy. Instead of looking for planets that look like Earth, we must learn to read the chemical story written in their light. The definitive biosignatures we seek must be based on atmospheric chemistry, not on visual resemblance. This means that the presence of water vapour, methane, DOT, or oxygen in an atmosphere is not enough on its own. We have to look at the context, the ratios, DOT, and the presence of other compounds that tell the full story. For instance, finding water vapour alongside massive amounts of silicate vapour would immediately flag a world as sterile, no matter how Earth-like it might seem from a distance. This leads to the concept of anti-biosignatures, or, more accurately, signatures of abiogenic processes. These are chemical combinations that scream hostile environment. The silicate haze of HD 189733b is a prime example. A thick atmosphere rich in vaporized rock is a clear indicator of temperatures far too high for any known biochemistry to survive. Other abiogenic signatures could include certain ratios of carbon monoxide to carbon dioxide, or the presence of particular sulfur compounds in abundance, which would point to volcanic activity or photochemistry that precludes life. By actively searching for these negative indicators, we can quickly filter out the obvious dead ends, saving precious telescope time and computational resources for the most promising candidates. This planet also underscores the immense value of studying the entire spectrum of planetary environments, especially the most extreme ones. Before we discovered worlds like this, our understanding of habitability was largely based on the conditions in our own solar system. We had the rocky, life-bearing worlds of the inner system and the cold, gaseous giants of the outer system. HD 189733b shatters that limited perspective. It shows us that planets can exist in states of perpetual, global violence that we never imagined. By studying these extremes, we are effectively mapping the outer boundaries of what is possible. We are defining the edges of the habitable zone not just in terms of temperature and distance, but in terms of atmospheric dynamics, stellar activity, and chemical stability. Understanding why this world is so hostile helps us better understand why Earth is so hospitable. It highlights the delicate balance of factors that make our planet a haven: a stable star, a protective magnetic field, a robust atmosphere with the right composition, and an orbital distance that allows for liquid water. This comparative planetology is essential. Every hellish world we discover and characterize adds another data point, helping us create more accurate models of planetary evolution and climate. These improved models are then used to interpret the flood of data from current and future telescopes. When the James Webb Space Telescope or the upcoming Extremely Large Telescope observes a distant exoplanet, the algorithms that analyze its atmosphere will be informed by what we learned from HD 189733b. We will have a better grasp of how to distinguish between a spectrum that suggests a temperate, rocky world and one that indicates a scorching, silicate-clouded inferno. This refinement is a continuous process. As we get more data from this planet and others like it, we can test and improve our simulations of fluid dynamics, radiative transfer, and photochemistry under extreme conditions. This makes us better at predicting a planet's climate from limited data. For example, if we see evidence of a strong temperature difference between a planet's day and night side, we can infer the likelihood of powerful winds, which in turn might affect cloud formation and atmospheric mixing. This deeper understanding directly impacts which worlds we flag for further study. In the vast catalogue of exoplanets, we need a way to prioritise. The lessons from this deadly world help us create a scoring system where planets are ranked not just on their potential for liquid water, but on a multitude of factors including stellar activity, atmospheric composition, and climate stability. A planet that shows signs of abiogenic signatures like silicate clouds would be deprioritized, while one with a chemical equilibrium suggestive of biological processes would move to the top of the list. This makes the search for life more efficient and scientifically rigorous. Ultimately, HD 189733b is a humbling reminder of the universe's nature. It is a place of immense variety and, often, immense hostility. The cosmos is not designed for our comfort or convenience. It is a physical realm governed by laws that can create breathtaking beauty and unimaginable violence in equal measure. This planet embodies that duality perfectly. A beautiful blue marble hiding a core of chaos. This perspective is crucial for maintaining a balanced and realistic outlook in astrobiology. While it is exciting to be optimistic about finding life, it is equally important to accept that barren, hostile worlds may be the norm, and habitable oases like Earth might be rare. This doesn't make the search less meaningful. It makes a potential discovery all the more significant. By learning from worlds like HD 189733b, we are not being pessimistic. We are being smart. We are arming ourselves with the knowledge to see through cosmic illusions and focus our efforts on the most promising targets. In doing so, we honour the scientific process, embracing all data, especially from the most alien and unforgiving environments, to guide us on this incredible journey. The implication is clear. The path to finding life may very well be paved with the lessons we learn from worlds where life is utterly impossible, while the search for life teaches us to look beyond appearances and value chemical clues over visual ones. Let's push our imagination to its limit and consider what it would actually be like to stand on, or rather within, this world ourselves. The very idea of a manned mission to HD 189733b is the stuff of pure science fiction, a fantasy that would end in instantaneous and catastrophic failure. Any spacecraft humanity could ever build would be torn apart long before it even reached what we might loosely call the upper atmosphere. The approach alone would be fraught with peril, as the planet's proximity to its star means navigating an intense barrage of stellar radiation and gravitational forces. As our hypothetical ship drew closer, the visual would shift from a distant blue dot to a swirling, angry marble of deep azure and fiery orange, a warning sign of the chaos within. The initial entry into the exoplanet's atmosphere would be the final moment of existence for the vessel. The friction from plunging into the dense, hydrogen-rich air at orbital velocities would generate temperatures far exceeding those of a meteor entering Earth's atmosphere. The heat shield would vaporize in seconds, followed by the metal hull melting and then boiling away into a cloud of ionized gas. The immense pressure, combined with temperatures soaring above 1000 degrees Celsius, would ensure that no recognizable piece of the ship or its occupants would remain. It would be a dissolution into the very elemental soup that makes up this hellish environment. A swift and violent end. But let's engage in a thought experiment. A piece of impossible magic where we could somehow be placed intact into a relatively stable layer within this raging atmosphere. The first thing that would overwhelm you would be the light, or rather, the lack of familiar light. You would be enveloped in a dim, oppressive glow, a hellish twilight of deep reds, oranges, and yellows. This is not sunlight as we know it. It is the incandescent glow of the superheated atmosphere itself, a world so hot that the air shines with its own thermal radiation. Looking up, the sky would be dominated not by a friendly sun, but by a colossal, swirling sphere of orange fire, the parent star HD 189733. It would appear gigantic, many times larger than our sun in the sky, its surface a churning cauldron of sunspots and magnetic storms, a constant, menacing presence. There would be no day or night cycle, no sunrise or sunset, just this eternal, fixed orange eye staring down from the heavens, pouring unimaginable amounts of energy into the atmosphere below. The heat would be in physical, crushing force. It wouldn't just be hot, it would be a pervasive, baking intensity that would cook you from the inside out. Every breath, if it were even possible to breathe, would sear your lungs. The air itself a mixture of scorching hydrogen, helium, and the toxic vapours of vaporized metals and silicates. Then there is the sound, or more accurately, dot, the noise. It would be the most deafening, overwhelming roar you could possibly conceive. This is not the sound of wind. It is the sound of a continuous, planetary scale explosion. The supersonic winds, screaming at over 8,000 kilometers per hour, would create a constant, deep-throated thunder that vibrates through your entire body. It would be so loud that it would be physically painful, a pressure on the eardrums that threatens to burst them, a rumble so profound you would feel it in your bones more than hear it with your ears. There would be no other sounds, no birds, no rustling leaves, no distant waves, just this unending, mind-shattering howl of a world in perpetual agony. Within this roar, there would be other sharper, more violent noises. The crackle and sizzle of electrical discharges would rip through the air. But these wouldn't be ordinary lightning bolts from water clouds. Here, the lightning would be generated by the intense friction between countless trillions of charged silicate particles. These electrical storms would be permanent, flashing all around you with a sharp, blue-white light, illuminating the swirling, abrasive haze in sudden, terrifying bursts. Each flash would reveal the true horror of the environment for a split second before being swallowed again by the gloom. And then you would see the rain. It would not fall from above, driven by those hypersonic winds. The precipitation would be a horizontal, blasting sheet of glass. At first, it might look like a shimmering, beautiful mist, but that beauty is a lethal illusion. This is a storm of microscopic shards of solidified glass, each particle sharp and jagged from its rapid, turbulent formation, moving at ballistic speeds. This rain would act like a perpetual sandblaster on a cosmic scale. It would scour and erode any surface instantly, if you could extend your hand. The skin would be stripped away to the bone in a fraction of a second. The particles themselves would range in size from fine dust to larger, needle-like fragments, all whipping through the air in a dizzying, chaotic dance. The glass would not be clear like window pane. It would likely be coloured by impurities of iron and other metals, giving the storm a faint, eerie glow as it reflected the incandescent light of the atmosphere and the flashes of silicate lightning. This is not a weather event that starts and stops. It is the permanent state of the planet. There is no calm, no eye in this storm. The entire atmosphere is the storm. The physical sensations would be beyond any human experience. The wind alone would exert a force greater than any hurricane on Earth, making it impossible to stand or even orient yourself. You would be tossed and hurled through the chaotic currents, a speck in a global river of fury. The pressure would be immense, crushing, making every movement a struggle against an invisible, weighty fluid. The combination of heat, noise, and abrasive wind would create a sensory overload that would quickly lead to disorientation and shock. There would be no up or down, No left or right, only a maelstrom of violence in every direction. The very air you are trying to move through is thick, dense, and hot, offering resistance like trying to swim through molten lead. Your body would be simultaneously baked, blasted, and shredded. The concept of a surface is meaningless here. As a gas giant, there is no ground to land on. You would simply fall or be carried deeper into the atmosphere, where the temperature and pressure rise to even more extreme levels, eventually reaching conditions where matter behaves in ways we cannot even simulate. Long before that, any protective suit or technology would have succumbed to the relentless assault. The glass rain would have eroded its outer layers, the heat would have melted its internal components, and the pressure would have crushed its structure into a crumpled wreck. This imaginary journey underscores the pure, unadulterated power of natural forces operating without any constraint. HD 189733b is not evil or malicious. It is simply a physical system following the laws of thermodynamics and fluid dynamics to their most extreme conclusions. It is nature in its most raw and indifferent form, a place where the concepts of comfort, safety, and life are not just absent but are physically impossible. The planet does not care about your presence. It would destroy you not out of anger, but simply because you are there, an insignificant anomaly in its perpetual, self-sustaining cycle of vaporization and condensation. This thought experiment, while terrifying, is valuable. It translates the dry data of spectroscopy and wind speed measurements into a visceral, human experience. It helps us comprehend the scale of the violence we are detecting from 63 light-years away. We can read about temperatures of 1,000 degrees and winds of 8,000 kilometers per hour. But imagining the sight, sound, and feel of that environment drives home the true meaning of those numbers. It reinforces why this world is such a powerful teacher in our search for life elsewhere. It is the ultimate control sample, a data point of pure hostility that makes us appreciate the delicate, fragile balance of our own planet all the more. The silent, airless vacuum of space is often seen as the most hostile environment, but HD 189733b presents a different kind of hell, one that is vibrant, loud, and seething with energy. A constant, raging testament to the fact that the universe can be violently, beautifully, and utterly uninhabitable. After that harrowing imaginary descent into its atmosphere, it is a profound relief to return to the safe, distant perspective of Earth-based observation. And the exciting truth is that the story of HD 189733b is far from over. This world will continue to be a prime target for astronomers for decades to come. A celestial laboratory that promises to reveal even more secrets with every new technological advancement. The reason is simple. It is one of the best characterized exoplanets we have, a benchmark against which we can test our theories and instruments. And with a new generation of observatories coming online, we are poised to learn things about it that were pure science fiction just a few years ago. The star player in this new era is, without a doubt, the James Webb Space Telescope. Its incredibly sensitive infrared instruments are a perfect match for studying a hot world like this. While Hubble gave us our first breathtaking clues about the atmosphere, Webb is going so much deeper. It is not just taking a quick look, it is performing a deep, forensic analysis. The spectra it is collecting are of a resolution and precision we have never had before. This allows scientists to do more than just confirm the presence of water vapour or silicate particles. It lets them measure their abundances with much greater accuracy. They can look for trace gases that were previously undetectable, Perhaps new metal vapours or other exotic compounds that form in the extreme heat. This is like moving from a grainy black and white photo to a full colour, high-definition video. We are not just confirming the ingredients of the atmosphere, we are learning their exact proportions and how they vary with altitude. This detailed chemical census is crucial for understanding the complex chemical reactions driven by the intense stellar radiation, helping us build a more complete picture of the planet's atmospheric chemistry. But the future does not stop with Webb. Here, on the ground, a new behemoth is rising, the extremely large telescope. With a primary mirror spanning 39 metres, it will collect an immense amount of light, allowing for a different kind of observation. One of the most ambitious goals for telescopes like the ELT is to attempt to directly image exoplanets. But for a world as close to its star as HD 189733b, that remains incredibly challenging. However, its power will be used in a more ingenious way. During a transit, the ELT could potentially perform spectroscopy on different parts of the planet's atmosphere as it crosses the star's face. This would allow astronomers to create a crude but revolutionary map. They could, for instance, measure the composition and temperature of the atmosphere over the permanent day side versus the terminator, the line between day and night. This would give us our first ever two-dimensional view of an exoplanet's climate system. We could see how the silicate cloud cover changes from the hot day side to the slightly cooler night side, directly testing our models of how these clouds form and dissipate. Furthermore, by observing the planet throughout its entire orbit, not just during transit, the ELT could help create a more detailed map of the temperature distribution across its atmosphere. This would provide unprecedented data on how efficiently those supersonic winds are actually moving heat from the day side to the night side. It would be like getting a weather satellite view of a world 63 light years away. All this new data is not an end in itself. It is fuel for the sophisticated computer models that simulate planetary climates. Right now, scientists have models that try to replicate the winds, the temperature extremes, and the glass rain, but these models are based on limited data. With the flood of information from Webb and the ELT, these models can be refined and made vastly more accurate. Researchers can input the new dot, precise measurements of atmospheric composition and temperature, and see if their simulated planet develops winds of 8,000 kilometers per hour and global silicate storms. If the model's prediction matches the new, exquisite data, we know we are on the right track. If it does not, it forces us to rethink our assumptions, perhaps about how energy is transferred in the atmosphere or how clouds interact with light and heat. This process of observation and simulation is a self-correcting cycle that steadily improves our understanding. This is not just about understanding one weird planet. It is about stress testing our fundamental physics. The conditions on HD 189733b are so extreme that they push the laws of thermodynamics and fluid dynamics to their limits. By getting our models to work for this world, we make them more reliable for all worlds, including potentially habitable ones. The physics of cloud formation, for example, is notoriously complex. By studying the simple, if violent, silicate clouds of this hot Jupiter, we can improve how we simulate the water clouds of Earth-like exoplanets, which is essential for assessing their true habitability. Another thrilling prospect is studying the planet's atmosphere in real time during stellar flares. We know its star is active and prone to eruptions. With the continuous monitoring capabilities of new space telescopes and the rapid response times of ground-based observatories, astronomers hope to catch the planet in the act of being hit by a massive flare. They would observe the system just before, during, and after the flare event. The goal would be to see how the planet's atmosphere responds. Does the upper atmosphere heat up and expand dramatically? Does the rate of atmospheric escape spike? Does the chemical composition change as the intense UV and X-ray radiation breaks apart molecules and creates new, transient ones? Watching this dynamic process would be like conducting a natural experiment, showing us how a planetary atmosphere evolves under a sudden, intense blast of energy. This has huge implications for the potential for life on planets orbiting active stars, especially the common red and orange dwarfs. If a flare can strip away a gas giant's atmosphere, it would be devastating for a smaller, rocky world. HD 189733b offers a front row seat to these violent interactions. The ultimate goal of all this observation is to move from a static picture to a dynamic movie. We want to understand HD 189733b not as a snapshot, but as a living, breathing, and seething world with a climate that changes over time. We want to understand its weather patterns in the same way we understand Jupiter's bands and storms. Does it have permanent jet streams? Are there variations in the glass rain intensity? How does the atmospheric circulation respond to the cyclical activity of its star? Each new observation adds a frame to this movie. The journey from its discovery as a faint dip in starlight to a world with a mapped climate is one of the great stories of modern science. It demonstrates our relentless curiosity and our ever-increasing ability to explore the cosmos without ever leaving our home planet. The future of observing this particular world is a microcosm of the future of exoplanet science as a whole. The techniques we perfect here, the models we validate, and the questions we learn to ask will all be applied to the thousands of other exoplanets we have discovered. HD 189733b is our training ground, our reference point, and our reminder of the astonishing diversity of planets in our galaxy as we peer deeper into its raging atmosphere with each new telescope. We are not just learning about one distant world. We are learning how to see, understand, and ultimately appreciate the countless other worlds waiting to be studied. The investment in studying this hellish planet pays dividends across all of astronomy, making us better, more discerning explorers of the universe. Its value lies not in its potential for life, but in its perfection as a natural laboratory for extreme physics, a role it will continue to play for many years to come, constantly challenging our assumptions and expanding our knowledge of what is possible. While our future observations will undoubtedly reveal stunning new details about this world, those very observations are also chronicling its slow, inevitable demise. The intense radiation and blistering heat from its star are not just shaping HD 189733b, they are actively dismantling it, in a process so dramatic that we can almost watch it happen in real time. This phenomenon is known as hydrodynamic escape, and it is essentially the planet's atmosphere boiling off into space, a fate that likely awaits many of the so-called hot Jupiters we have discovered. The mechanism works because the upper layers of the planet's atmosphere are being superheated by the star's high-energy ultraviolet and X-ray radiation. This isn't just a little warmth. It's enough energy to give the gas molecules such a tremendous thermal velocity that they exceed the planet's escape velocity. On a world with weaker gravity or a quieter star, these molecules would be trapped. But here, the combination of intense heating and the planet's own substantial but finite gravity creates a perfect storm for atmospheric loss. Think of it like a comet approaching the sun. You see that glorious tail of gas and dust being blown away by the solar wind. HD 189733b is experiencing a similar, but far more massive and continuous, version of that process. The planet is so close to its star that it is effectively sitting in a stellar furnace, and its outer atmosphere is being cooked and stripped away layer by layer. The primary component being lost is hydrogen, the lightest and most abundant element in the planet's composition. As the upper atmosphere heats up, the hydrogen atoms gain enough energy to achieve escape velocity, flying off into the void. This isn't a gentle seepage, it's a hydrodynamic flow, a river of gas streaming into space. Astronomers have found strong evidence for this by observing the planet in a specific wavelength of ultraviolet light that is absorbed by hydrogen. During a transit, they detected a much larger and extended dip in the star's light in this UV band than in visible light. This indicated that a vast cloud of hydrogen, a bloated envelope, was surrounding the planet and extending far beyond its main atmospheric body. This cloud forms a long, comet-like tail, trailing behind the planet as it speeds along its orbit. This tail is the direct, observable signature of the planet's atmosphere evaporating before our eyes. The process is not always constant. It is likely intensified during the star's frequent and powerful flares. A single, massive coronal mass ejection or a strong X-ray flare can deliver a catastrophic pulse of energy to the planet's atmosphere, dramatically increasing the heating and potentially blowing off a huge volume of gas in one go. These stellar tantrums act like a hammer, chipping away at the planet's gaseous envelope in violent, episodic bursts alongside the steady, background simmering. The rate of this evaporation is a key area of study. Scientists use complex models to estimate how much mass the planet is losing every second. While the numbers are astronomically large in human terms, think millions or billions of kilograms per second in the context of a gas giant's total mass, it is still a slow process. The planet is not going to disappear tomorrow. However, over the course of billions of years, this relentless stripping can have profound consequences. The evolution of a planet is a battle between its formation and the forces that seek to erode it. For a hot Jupiter like this one, the erosion is a dominant force. The key factor determining its ultimate fate is the balance between the stellar radiation driving the escape and the planet's gravity trying to hold on. A more massive planet has a stronger gravitational grip, making escape harder. A planet closer to a more active star will experience a stronger driving force. HD 189733b, with its close orbit and active host star, is in a particularly vulnerable position. So what is the endgame? If this process continues unabated for the entire lifetime of the star, it could, in theory, completely strip away the planet's massive hydrogen and helium envelope. What would be left? Astronomers speculate that the final result could be an exposed rocky or metallic core, a so-called Chthonian planet. This would be the skeletal remnant of a gas giant, a world that was once a majestic king of its system reduced to a barren, scorched core. Imagine a planet-sized ball of rock and metal, perhaps 10 times the mass of Earth, orbiting impossibly close to its star, still tidally locked and still blisteringly hot, but now devoid of its magnificent and violent atmosphere. No more supersonic winds, no more silicate clouds, no more glass rain, just a silent, super-dense cinder, period, the ghost of a giant. This hypothetical fate connects the dots between gas giants and terrestrial planets, suggesting a possible evolutionary pathway. It is a stark reminder that planets are not static objects. They are dynamic systems that change dramatically over time. Studying this evaporation process on HD 189733b is therefore about more than just understanding one planet's future. It is about understanding the life cycle of a whole class of exoplanets. There are thousands of hot Jupiters out there, and this one serves as a nearby template for what might be happening to all of them. By measuring its mass loss rate and correlating it with stellar activity, we can create models that predict the survival chances of other similar worlds. This research also has implications for smaller, rocky planets. A rocky world in a close orbit around an active star could have its atmosphere completely stripped away, transforming it from a potential habitat into an airless, sterile rock. The study of hydrodynamic escape on this gas giant provides a foundational understanding of the physical processes that can make or break a planet's atmosphere. As we continue to observe this world with telescopes like Hubble and James Webb, we will get better and better measurements of the composition and dynamics of its escaping atmosphere. We might detect other elements besides hydrogen in the tail, such as oxygen or carbon, which would tell us even more about the interior composition and the chemical processes at work during this great escape. Each new observation adds a piece to the puzzle, helping us to forecast the long-term future not only of this fascinating world, but of countless others like it throughout the galaxy. The slow evaporation of HD 189733b is a dramatic, real-time lesson in planetary evolution, a vivid demonstration of the powerful and often destructive relationship between a star and its planets, while the slow, cosmic disintegration of this world is a fascinating process to observe. It underscores a much deeper truth. Studying a seemingly inhospitable hellscape like HD 189733b is of incalculable scientific value precisely because it operates as a natural laboratory for testing the laws of physics under conditions we could never hope to recreate on Earth. Our home planet offers a relatively narrow band of temperature and pressure, a comfortable niche where life thrives, but the universe is under no obligation to be so gentle. This exoplanet throws all those comfortable assumptions out the airlock, presenting us with an environment where temperatures soar high enough to vaporize rock, winds move faster than sound, and the very rain is made of glass. For a physicist, this isn't a nightmare. It's the ultimate playground. The extreme conditions allow us to probe the fundamental behavior of matter and energy in regimes that defy intuition. We can study fluid dynamics in a super-rotating atmosphere where the entire planet is a single, raging storm cell. We can observe heat transfer on a global scale, driven by a permanent, colossal temperature difference between day and night sides. We can investigate the chemistry of silicates not as solid rocks, but as vapors and molten droplets, understanding how they nucleate, condense, and form clouds in a seething hydrogen soup. These are not abstract thought experiments. We have real data from a real world that we can use to stress test our most fundamental theories. The equations for fluid flow or radiative transfer are the same everywhere. But seeing them play out on this colossal and violent stage validates their universality and reveals their consequences in ways no computer simulation conceived in isolation ever could. The practical benefits of this are immense and directly impact our understanding of our own world. By refining our complex computer models to accurately replicate the insane weather patterns and atmospheric chemistry of HD 189733b, we are inevitably improving the very same tools we use to simulate the climate of Earth. The physics of cloud formation, for instance, is a notorious challenge in climate science. Our models have to account for how water vapor condenses, how clouds reflect sunlight, and how they trap heat by studying the simpler, if more extreme, silicate clouds on this exoplanet. We can test and improve the core algorithms that describe nucleation and particle growth. Getting the model to correctly predict the global distribution of silicate haze on a world 63 light-years away gives us greater confidence in its predictions about cirrus clouds or hurricane formation in our own atmosphere. Furthermore, Understanding how an atmosphere transports heat from a hot region to a cold one with such ferocious efficiency helps us refine our models of atmospheric circulation for all planets. This knowledge is not just academic. It makes us better at predicting weather patterns, understanding past climate change, and modelling the potential futures of other worlds, including those that might be habitable, when we look at a rocky exoplanet in a star's habitable zone. The lessons learned from this hellish gas giant help us interpret its spectrum. We become better at distinguishing between a climate stabilised by biological processes and one that is a sterile, runaway greenhouse, all because we have a baseline understanding of how atmospheres behave under extreme stellar forcing. Beyond improving our models, HD 189733b serves as an essential reference point, a crucial data point in the vast and growing catalogue of exoplanets. Before we found worlds like this, our understanding of planetary science was almost entirely based on our own solar system, which we now know is just one possible configuration among billions. This planet single-handedly expanded our definition of what is possible. It showed us that a gas giant can orbit breathtakingly close to its star, that a planet can be tidally locked, and that weather can be a permanent, global cataclysm rather than a temporary disturbance. It provides a benchmark against which we can compare other hot Jupiters. Is its wind speed typical? Are its silicate clouds common? By having such a well-studied example, we can start to categorize the incredible diversity of worlds in our galaxy. It helps us see the broader patterns, to understand how a planet's characteristics, its mass, dot, its orbit, the type of its star, shape its environment. This classification is fundamental to science. We can't understand the rule if we only know the exceptions. And HD 189733b helps define the outer boundaries of the rulebook. It represents one end of the spectrum, a world where physical processes are pushed to their absolute limits. And by understanding this extreme, we gain a better perspective on the entire population of exoplanets. It teaches us that our solar system, with its calm giants and neatly separated orbits, is not the default. It is merely one possibility in a cosmos teeming with much more dynamic and violent systems. This research also acts as a powerful engine for technological and methodological innovation. The sheer difficulty of observing and characterizing a world so far away pushes our instrumentation and our ingenuity to their limits. Detecting the faint signature of silicate particles in the light of a distant star requires telescopes of exquisite sensitivity and stability. It forces us to develop new and more precise methods for calibrating instruments, for removing noise from data, and for processing the incredibly weak signals we receive from across the light years. The techniques of transit spectroscopy and emission spectroscopy, which were once cutting edge, have been honed and perfected through the study of targets like this one. The drive to understand this planet has contributed to the scientific case for building more powerful observatories, like the James Webb Space Telescope and the upcoming Extremely Large Telescope. These instruments are not built in a vacuum. They are designed to answer specific, compelling questions about the universe. And the bizarre nature of HD 189733b provides some of the most compelling questions of all. The challenge of interpreting the data forces us to develop more sophisticated computer models and data analysis algorithms. In a very real sense, the need to understand this alien world accelerates our ability to explore all the others. It forces us to be more creative, more precise, and more clever in our approach to remote sensing. Ultimately, the greatest value in studying this inferno is the profound philosophical lesson it teaches. Understanding the extremes is absolutely fundamental to understanding the norm. we cannot truly appreciate what makes Earth a living, breathing world without also understanding what makes other worlds dead and hostile. The calm balance of our climate, the gentle cycle of water-rain, the protective blanket of our atmosphere, these are not cosmic guarantees. They are the result of a specific and delicate set of circumstances. By confronting the unbridled violence of HD 189733b, we gain a deeper appreciation for the fragility and rarity of our own planetary home. It provides the necessary contrast that makes the habitable zone meaningful. It defines the boundaries of hostility, so we can better recognize the signs of hospitality. The search for life elsewhere is not just about finding planets that look like Earth. It is about systematically ruling out all the worlds that are like HD 189733b. Its existence makes our search more focused, more efficient, and more profound. So, while we may never set foot on this glass-raining giant, and while it may slowly evaporate into nothingness over eons, its legacy is secure. It has taught us more about the laws of physics, the diversity of planets, and the capabilities of our own technology than any number of placid, Earth-like worlds ever could. It is a reminder that in science, there is no such thing as a useless data point, and that sometimes the most valuable worlds to study are the ones that are the most terrifyingly alien. The profound scientific lessons we learn from this world are crucial, but they are not the whole story. The moment the true nature of HD 189733b was revealed, a blue planet with sideways glass rain, it instantly transcended the realm of pure science and ignited the public imagination, rapidly becoming an icon of cosmic weirdness and a staple in popular culture. This is a world that feels like it was pulled directly from the pages of a pulp science fiction novel. A concept so vividly alien that it demands to be used as a backdrop for stories. And that is exactly what has happened. Writers and filmmakers have seized upon this planet as the ultimate setting for narratives exploring themes of impossible survival, sheer cosmic horror, and the humbling insignificance of humanity when faced with the universe's raw, indifferent power. It is the perfect death world. A place where the environment itself is the antagonist, a character of pure, unrelenting fury. In these stories, it serves as the final, insurmountable obstacle for explorers, a prison planet for the most dangerous criminals, or the lair of an ancient, unknowable alien entity that thrives in conditions we cannot even endure. Its very existence provides a scientifically plausible foundation for the most extreme forms of speculative fiction, grounding terrifying concepts in real, observed data. This cultural journey begins with the process of translation. The dry, technical data from scientific papers, spectral lines indicating silicates, Doppler measurements of wind speed, needs to be converted into something visceral and emotionally impactful. This is the role of documentary filmmakers and concept artists. They take these numbers and transform them into stunning visual and narrative experiences. Through sophisticated computer-generated imagery, we see swirling, cobalt skies dominated by a massive, angry orange star. We witness tempests of glittering, razor-sharp glass shards moving as a horizontal blur, lit from within by the constant flash of electrical storms. We hear the deep, simulated roar of supersonic winds, a sound designed to convey a scale of violence beyond human comprehension. This artistic interpretation is not just for show. It is a vital bridge between the scientific community and the public. It makes the abstract real, turning HD 189733b from a data point into a destination, a place that, while terrifying, we can visually and emotionally explore. This process brings cutting-edge astronomy directly into people's living rooms, sparking wonder and curiosity in a way that a graph of atmospheric composition never could. It demonstrates a public appetite not just for discovery, but for genuinely alien discoveries that challenge our preconceptions of what a planet can be. This planet perfectly embodies a powerful and paradoxical idea, the concept of deadly beauty. It is a world with a deep, captivating azure hue, a colour we instinctively associate with serenity and life. Yet this beauty is a lethal mirage. This duality is incredibly compelling. It inspires both awe and fear simultaneously, a mix of emotions that is at the heart of much great science fiction and horror. It plays on the deep-seated human fear of deception, that something which appears safe and familiar can be utterly hostile underneath. This makes it a potent symbol, a reminder that the universe is not designed for our comfort or even our comprehension. It can create things of stunning visual splendor that are, in their very nature, absolutely incompatible with our existence. This moves the planet beyond a simple setting and into the realm of a metaphor for the unknown dangers that might lie in wait among the stars, or even for the destructive yet beautiful forces of nature here on Earth. The widespread popularity of this particular exoplanet is also a telling sign of the public's evolving interests. It shows that there is a growing appetite for science that is not just about finding another Earth, but about discovering the true, bizarre diversity of the cosmos. People are fascinated by the outliers, the exceptions, the worlds that defy all our expectations. HD 189733b is the antithesis of Earth, and that is precisely what makes it so memorable. It proves that the universe is far more creative and unpredictable than we are. Its story is a perfect antidote to scientific anthropocentrism, the idea that everything revolves around our own experience. This planet has become a cultural symbol for the vastness, strangeness, and impenetrability of creation. It is a placeholder for all the wonders and horrors we have yet to discover. A single, well-defined example of the infinite possibilities that exist in the galaxy. In a way, this cultural journey completes the scientific one. The data is gathered, analysed, and published. But its journey isn't over until it filters into the broader cultural consciousness. HD 189733b has achieved this. It is not just an object of study for astronomers. It is a source of inspiration for artists, a catalyst for storytellers, and a topic of wonder for anyone who looks up at the night sky and ponders what might be out there. It has become a shared reference point, a world that people can point to and say, "Look, Dot, the universe is capable of that." This transformation from scientific datum to cultural icon ensures its legacy, long after the specific details of its atmospheric composition have been refined by newer telescopes. The core image of a blue world with glass rain will endure in our collective imagination. It stands as a powerful testament to the fact that the most impactful scientific discoveries are those that not only expand our knowledge, but also capture our spirit, challenging us to imagine the impossible and reminding us that reality, especially out there among the stars, is often stranger and more spectacular than fiction. The vivid imagery of glass rain that so captivates our imagination naturally leads to a more grounded, chemical question. Dot. Why glass? On Earth, the same silicate materials can form either the structured crystals of sand or the chaotic, amorphous solid we know as glass. The answer on HD 189733b lies not in the material itself, but in the brutal speed and violence of the environment. A quenching process so rapid it literally freezes the atomic structure in a state of disordered chaos. The journey begins with the raw material, silicate vapour in the upper atmosphere. This vapour, having been boiled off from the planet's scorching dayside, is carried by those immense winds to slightly cooler altitudes. Here, the temperature drops just enough for the vapor to condense, but it doesn't condense into solid grains. It condenses directly into countless trillions of microscopic droplets of liquid silicate, a superheated mist of molten rock. This is the first critical step. Now, on Earth, if you were to take this molten silica and let it cool down slowly and peacefully, the atoms would have the time and energy to arrange themselves into a neat, repeating, crystalline pattern. This is how minerals like quartz form, with their atoms locked into a precise, three-dimensional lattice. This orderly structure is what gives sand its granular, crystalline nature. But the atmosphere of HD 189733b is the absolute antithesis of slow and peaceful. The newly formed droplets of molten glass are instantly seized by the hypersonic winds, which whip them through the atmosphere at thousands of kilometers per hour. This creates an environment of extreme turbulence and rapid heat loss. The droplets are surrounded by a chaotic maelstrom of other gases and particles, and they are moving from hot zones to cold zones and back again in a matter of seconds. This rapid, violent cooling is the key to glass formation. The process is known as quenching. As the liquid silicate droplets are blasted through the cooler parts of the atmosphere, they lose their thermal energy so quickly that the atoms simply do not have time to move into the stable, low-energy positions of a crystal lattice. They are frozen in place, locked into the random, disordered arrangement they had in the liquid state. It is a bit like trying to organize a crowd of people into neat rows during a hurricane. The chaotic external forces prevent any order from being established. The result is a solid, but one without long-range order, a glass. This is exactly how we create artificial glass on Earth. By cooling molten silica so quickly that crystallization cannot occur. The natural version of this on Earth is volcanic glass, like obsidian, which forms when lava cools rapidly upon contact with air or water. On this exoplanet, the entire planet's atmosphere acts as a giant, continuous quenching chamber. The absence of a stable, slow cooling environment is therefore the second critical factor. There is no calm surface upon which these droplets can settle and slowly solidify over thousands of years. There is no peaceful pool of magma cooling deep underground. The silicate material is perpetually in motion, from vapor to liquid to solid and back to vapor again, all within a violently churning atmospheric fluid. This constant state of flux and extreme turbulence actively prevents the nucleation and growth of crystals. For a crystal to begin forming, a small cluster of atoms, a nucleus, must first arrange itself in the crystalline pattern, and then other atoms must have the time and stability to add themselves to this growing structure. In the chaotic, wind-sheared environment of this planet's sky, any such nascent crystal nucleus is immediately torn apart or cooled so rapidly that the growth process is aborted before it can even properly begin. The impurities present in the atmosphere, such as iron or magnesium, also play a role. These metal atoms can get mixed into the silicate droplets as they form. In a slow cooling scenario, these impurities might be excluded from the growing crystals or form their own distinct mineral phases. But in the rapid quenching process, they become trapped within the amorphous glass structure. These impurities can affect the properties of the glass, potentially giving it colour. Iron, for instance, could impart a greenish or bluish tint to the glass shards, which might contribute to the overall blue colour we see from a distance. As the scattered light interacts with these coloured, microscopic particles. So, the chemistry is a direct consequence of the physics. The same silicate material that makes smooth, rounded sand grains on a peaceful beach on Earth is forged into sharp, jagged shards of glass in the sky of HD 189733b because of the incredible speed of the solidification process. The wind is not just a transporter of the rain, it is an essential component of the manufacturing process itself. The extreme shear forces and rapid temperature fluctuations ensure that the solidification is instant and chaotic, guaranteeing that the resulting particles are not gentle grains of sand, but rather a deadly haze of sharp, abrasive, and irregular fragments. This is not a gentle geological process, it is a violent atmospheric one. It demonstrates how the same fundamental ingredients can yield radically different outcomes under different environmental pressures. The chemistry of glass formation on this world is therefore a perfect illustration of how planetary conditions dictate not just the weather, but the very nature of the matter that makes up that weather. It is a world where the sand itself is forged in a hurricane, and the result is a perpetual storm of countless tiny blades. The violent chemistry that forges glass instead of sand is just one part of a much larger, more fundamental redefinition we are forced to make when studying this world, the very concept of weather. On Earth, weather is a complex, dynamic system of transient events. A storm develops. It rains for a few hours. The sun comes out. Temperatures fluctuate between day and night, and seasons change over months. It is a system of patterns and cycles within a relatively stable and moderate overall climate. On HD 189733b, the word weather loses all of those familiar connotations. Here, weather is not a temporary state. It is the permanent, fundamental, and unchangeable condition of the entire planet. It is not a system of changes. It is a system of constants. The climate is not a complex interplay of many factors. It is a simple, brutal, and global cataclysm driven by a single, overwhelming engine. The insane temperature difference between the permanent day and permanent night sides. There are no seasons. There is no daily cycle of warming and cooling. There are no regional variations in the sense of one area having a calm climate while another has storms. The entire planet is locked in a single, furious weather pattern that never, ever ceases. The supersonic winds are not a weather event. They are the weather. The horizontal glass rain is not a storm. It is the permanent state of precipitation. The incandescent glow of the hot atmosphere is not a temporary condition. It is the perpetual lighting. This is a climate stripped down to its most elemental and violent form. This stands in stark contrast to Earth's climate, which is a complex system moderated by oceans, an atmosphere of just the right density, a protective magnetic field, and a rotational cycle that evenly distributes sunlight. Our weather is a delicate dance. On HD 189733b, the climate is a sledgehammer. The primary driver is simple and relentless. One side is incredibly hot. The other side is very hot. And the atmosphere screams in a continuous, desperate attempt to equalize the two. This creates a permanent, global river of air moving from the high-pressure day side to the low-pressure night side. There is no off switch for this process. The stellar radiation never lets up, so the heat pump never turns off. This results in an atmospheric dynamic that is, in a way, much simpler than Earth's. There are no meandering jet streams, no high and low pressure systems developing and dissipating, no fronts colliding. There is just the wind, a single, planet-encompassing torrent of gas that defines all atmospheric motion. This wind, in turn, dictates everything else. It determines where the silicate vapours go, where they condense into clouds, and how the resulting glass shards are distributed. The storms of glass are not discrete events that start and stop. They are a continuous, global bombardment that is as much a part of the environment as the air itself. If you were to somehow exist in this atmosphere, you wouldn't be waiting for a storm to pass because the storm is all there is. It is the baseline. This forces us to expand our definition of meteorology to include phenomena that are, for all intents and purposes, permanent and global. We are used to thinking of weather as something that happens in an environment on this planet. The weather is the environment. The constant, abrasive flow of particles, the unending roar of the wind, the perpetual temperature extreme. These are not perturbations to a calm state. They are the state itself. This has implications for how we classify exoplanets. A tidally locked planet like this operates on a completely different climatic principle than a rotating planet like Earth. Its meteorology is not about forecasting change, because the system is in a violent but steady state. The forecasting for this world would be trivial. Tomorrow, and every day after for billions of years, will be searingly hot with supersonic winds and horizontal glass rain. The concept of climate change here would refer to processes acting over geological timescales, like the slow evaporation of the atmosphere, not year-to-year variations in temperature or storm intensity. Studying this alien climate is therefore a lesson in extremes. It shows us the simplest possible outcome of a massive energy imbalance on a global scale. By understanding this pure, brutal system, we gain a better understanding of the fundamental principles of atmospheric physics. It is a climate in its most raw, unmoderated, and elemental form. There is no water cycle to complicate the energy balance, no biosphere to influence the chemistry, no complex topography to disrupt the flow. It is a pure hydrogen-helium silicate atmosphere responding in the most direct way possible to an unrelenting external heat source. This makes it an invaluable benchmark. When we look at other exoplanets, especially those that are tidally locked, we can use HD 189733b as a reference if we see signs of a strong day-night temperature contrast. We can infer the likelihood of powerful winds. If we detect silicate clouds, we can theorize about a permanent cycle of condensation and precipitation. This world provides the template for one end of the climatic spectrum. It represents a type of planetary environment where the weather is not a temporary feature but a permanent, defining, and global condition of relentless violence. A stark reminder that the peaceful, variable climate of Earth is a precious and perhaps uncommon exception in a universe capable of creating much simpler and much more hostile norms, having explored the permanent, violent climate that defines this world. It is almost a relief to turn to a topic that is, for now, firmly in the realm of pure speculation. Yet it raises fascinating questions about our far future. The unique composition of HD 189733b, specifically its atmosphere rich in vaporized silicates and other elements, naturally leads to a speculative but intriguing thought experiment. Could this hellscape ever be useful? The concept of interstellar mining, while currently the domain of science fiction, forces us to consider the practical implications of the resources we are discovering on alien worlds. In a purely theoretical sense, the atmosphere of this planet is a colossal reservoir of refined materials. The silicate vapors, if they could be harvested and condensed, represent a virtually unlimited supply of ultra-pure silica, the primary component of glass and a fundamental material in construction and manufacturing. Furthermore, the atmosphere likely contains significant amounts of vaporized metals like iron and magnesium, blown into the upper layers from the deep interior or from an evaporating core. These elements are the building blocks of any advanced civilization, essential for everything from infrastructure to technology. The sheer scale of the planet means the available quantity of these materials is astronomical, dwarfing any resource deposit we could ever find on Earth or in our solar system. The idea of tapping into such a vast, alien reservoir is, on a purely conceptual level, incredibly compelling. However, this is where the brutal reality of the environment slams shut any door of possibility for centuries, and likely millennia, to come. The technological challenges are so monumental as to be effectively insurmountable with any technology we can currently envision. The first and most obvious barrier is the extreme temperature. Any mining vessel or robotic probe would need to operate continuously in an environment hotter than a blast furnace, where temperatures are consistently high enough to melt and vaporize the very metals we would be trying to build the machinery from. Developing materials that can withstand such heat for prolonged periods, while also maintaining complex electronic and mechanical systems, is a challenge that likely requires breakthroughs in material science we have not even begun to approach. Then there are the winds. With sustained speeds exceeding 8,000 kilometers per hour, any physical structure would be subjected to forces far beyond what any engineering has ever been designed to handle. These are not gusts. They are a continuous, hypersonic river of gas that would tear apart any rigid structure or create unimaginable stresses on any kind of flexible harvesting apparatus. Simply maintaining a stable position in the atmosphere to conduct operations would be a feat of propulsion and control bordering on magic with our current understanding of physics. The third great barrier is the precipitation itself. The constant dot-war horizontal blasting of microscopic glass shards would create an environment of perpetual, extreme abrasion. Any surface exposed to this storm would be sandblasted into nothingness within hours, if not minutes. Protective shields would be eroded away faster than they could be replaced. Sensors would be scoured opaque, and moving parts would be jammed and ground into dust. The mining process itself is a puzzle. One highly speculative concept might involve not landing on a surface, but rather using specialized, incredibly resilient spacecraft that operate as atmospheric processors. These vessels would need to fly at specific altitudes, perhaps in the sweet spot where silicate vapors are condensing into droplets. They might use powerful magnetic or electrostatic fields to selectively draw in and concentrate these particles, condensing them into solid masses of glass or metal ingots within shielded internal chambers before transporting them out of the atmosphere. This avoids the need for physical drills or miners, but it requires a level of energy generation and technological sophistication that is pure fantasy today. The energy required for such an endeavour is another insurmountable hurdle. The journey to a planet 63 light-years away alone requires energy on a scale we cannot produce. Then, operating the mining vessels in that environment against such extreme forces would demand a power source of staggering magnitude, likely far beyond even mature nuclear fusion. When all these factors are considered, the impossible travel distance, the destructive temperatures, the shredding winds, the abrasive rain, and the astronomical energy demands, the economic case collapses completely. The cost of obtaining a single ton of silicate glass from HD 189733b would be so phenomenally high that it would make no economic sense whatsoever. Any material obtained would be the most expensive substance in human history, utterly impractical for any conceivable use. It would be far cheaper and easier to mine asteroids in our own solar system, or even to manufacture materials on Earth for the next 1,000 years. Therefore, the value in considering this idea is not practical, but philosophical. It forces us to think about the very long-term future of humanity and our relationship with the cosmos. It raises profound questions about ethics, property, and exploitation, if we ever became a species capable of such feats. Who would have the right to harvest the atmosphere of a world in another star system? What are the ethical implications of dismantling, or even altering, an entire planet, even one as hostile as this? Does simply having the capability grant the right? This speculative exercise uses HD 189733b as a case study for these larger questions. It is a placeholder for the kind of difficult discussions we may one day have to face if our technology and ambition ever truly reach for the stars. For now, and for the foreseeable future, this world remains what it has always been: a breathtaking scientific laboratory, a catalyst for our imagination, and a powerful reminder of the awe-inspiring and often hostile nature of the universe. Its value lies not in what we can take from it, but in what it teaches us about physics, planetary science, and our own place in the cosmos. The thought of mining it is a useful tool for stretching our minds, but the planet itself remains a pristine, if terrifying, monument to the raw power of nature, forever out of reach for exploitation, and forever secure in its role as one of the most fascinating and instructive worlds we have ever discovered.